I've already shortlisted the area of interest, Batapady Beach in Karnataka, India. As you can see on the Google search results, there are several search results which indicate that there is erosion on this beach. Let's open one news article. You can see that the erosion is particular on the Someswar Batapady stretch and it causes substantial damages. This is a video which shows the scale of destruction. Batapady Beach borders the Arabian Sea on the west coast of India. So now our objective is to visually discern where and how much the erosion is taking place. So let's go to Google Maps and search for the beach. As you can see, the beach feature has been demarcated on Google Map using a technique which is not known to me. But then, as you would see, that the feature is over the sea and not on top of the land. And you can see Someswar Beach and Batapady Beach, and we are particularly interested in the region between that. And you can see that there is blue sea below the demarcated stretch. Now this is unusual because let me just show you the satellite imagery and we can revalidate that the beach ends at a particular location, but the beach demarcation is at a completely different location. So it could be an, you can say, an error of satellite imagery demarcation, but then I'll present to you a contradicting example. Let's say Mandvi Beach, which is again on the west coast of India, and you see the demarcation over here. It is, the beach demarcation is reasonably accurate, and I'm pretty sure the other beaches also have a similar property. But then when we see Batapady Beach once again, it is not that accurate. So the problem with Google Maps is you can just get a static, you can say, depiction of that particular area of interest. You cannot do a time lapse of it. So for that we can go navigate to Google Earth Pro, which is a more advanced mapping software from Google. Over there, once we search the area of interest, we can perform not only a time lapse but also do some basic measurements. So you can see the Batapady Beach has been zoomed in and Airbus has captured this image in 2024, and the data has, to Airbus, has been provided by a few service providers, which is mentioned over there. Now Someswar Beach and Batapady Beach is the area of extent which we have zoomed into, and we can go to the time-lapse section, timeline section, and you can see that the imagery is available between 1985 to 2024, and one can scroll backwards to see the imagery available. So for example, this imagery is from 2022 February, and currently we have 2024 February imagery available with us. So now when you can do the time lapse, you can see how the area of interest, what kind of, whether it or not there has been a shift in the shoreline and whether or not there has been an erosion. So let's zoom into 2016, which is 8 years prior. You can straight away see that certain areas of the beach is full, whereas in 2024 it appears eroded. So let's zoom into a particular area. This is the area in 2024, how it looks like, and 8 years prior. Let's see how it is looking. Reasonably, you can say, much more fuller in size. So it clearly shows that there has been erosion, and if we go year by year, we can actually see what is the progression of it. But we'll use the ruler function and see that 42 feet is the size of the beach currently in 2024. The breadth of the beach, that is. But when we go to 2016, and if we just draw a new line, a rough estimation, you can see that it is 85 feet, 86 feet. So there's roughly, you can say, another 40 feet has been eroded over the span of 8 years, which is roughly 5 feet per year, which is a significant amount. So this is basically a visual check. It is not completely, you can say, accurate. It has a certain amount of approximation, but then it certainly is a good visual indicator for beginners and to understand what the area of interest is all about. Earth Observation or EO browser is a dynamic online platform developed by Planet Labs where one can access several satellite imagery data sources and even perform basic post-processing and analytics on the fly. We will do just so and create a time lapse which will allow us to see how a shoreline is developed over a period of time. You'll need to sign up for a free account on the portal in order to use the time-lapse feature. Let me show you the area of interest on Google Maps first. It lies on the southeastern coast of India in the metropolis of Chennai. On the satellite imagery view, let me zoom into the Marina beach, which is India's longest beach. This is how it looks. In particular, we will be keen to observe how the shoreline has evolved on the southern section of the beach. This portion lies on the confluence of the Adyar river, which deposits itself onto the Bay of Bengal. Back to the EO browser, we will select Sentinel-2 imagery as our data source. Operated by European Space Agency, this multispectral satellite constellation has a few distinct advantages. It is free of cost to use, has a wide geographic coverage, a high revisit time, as well as a high spatial resolution for Earth observation purposes. On the EO browser, we will type in Marina Beach on the Go to Place box. One advantage of this platform is one doesn't need to input coordinates or input the WKT file to select the area of interest. Just by typing out in the search box, we can basically find satellite imagery for that particular section. We'll select a period of 1 month from March to April 2024. We've already selected Sentinel-2 and we'll now hit the search button. The search results pop up with all the details. We will visualize one product. We now get the option to do a basic level of post-processing. So for example, false color demarcates area of natural vegetation very clearly. So on the fly, the imagery is processed and one can see the red section is vegetation. But we'll be interested to do NDWI, which is normalized difference of water index. In this particular, you can say modification of bands, what happens is the water features are clearly demarcated, as you can see. Now we will create a satellite imagery time lapse by clicking on that particular button on the right. So now it's very easy function to use. The particular area of interest, as I told you, is on the southern section of the beach, and this is where we'll center the you can say the particular box onto. Next, what we will do is go click the play button. A new section of the page opens up. In this, we have several options to choose from. One particular option which we'll have to take care of is we'll need to have a very low cloud coverage, because we don't want clouds to because it's an optical imagery, we don't want clouds to interrupt our, you can say, obstruct our findings. Now, the L2A product of Sentinel-2 is typically available from 2017 onwards. So we'll select 2017 to 2024 as our time period and hit the search button. All the search options are loaded, and on the right hand side at the bottom you can see that there are a sum total of 39 products which have been loaded. Now all these products are sorted on a monthly basis, as you can see on the top left section. So on each month, if the cloud cover matches, it shows a particular product. And now once we hit the play button, we can see how the satellite imagery has evolved. And you can see that on some sections, the Adyar river finds an outlet into the sea, whereas in some time their passage is blocked by the, you can say, beach. And the timeline is also shown on the top right section of the media which is being played on the browser. Isn't this a very cool feature? You can see one of the distinct advantages over Google Maps is, while the imagery on Google Maps is intermittent, but with Sentinel-2 you can find a very, you can say, frequent sources of satellite imagery. Now one particular reason why we selected this area of interest is because it was observed that there is accretion which takes place on the southern section of the beach. Now, typically, coastline erosion is treated as you can say, an adverse effect, but then accretion is also sometimes an adverse effect, because what happens is the Adyar river doesn't find an outlet into the sea, and basically the pollutants also stay back in the river instead of depositing it to the sea. So this is one of the reasons why we were keen to observe this particular area of interest. Now, while we had observed the NDWI, you can say playlist, we can also select another form of playlist. So this is your, you can say, true color, image, which looks like a normal photograph, optical photograph. And we can also, you can say, play around with the frames per second, etc. And we can see how the imagery has observed over this period of time which we had selected. We also have the option to download the imagery as a GIF file. And it's a very quick procedure. And while you can say we are not performing any high level technical analysis, but it definitely gives a very, very good context and much better than your Google Earth in order to see how the Marina beach has evolved. However, let me tell you that in Google Earth, because the imagery resolution is high, so for particular beaches, that is only preferable. In this example, I will use a different type of satellite imagery, namely radar imagery, to delineate the shoreline. In this article published in the Times of India on February the 9th of 2023, it is mentioned that around 30% of the coastline of Andhra Pradesh, a state on the east coast of India, is suffering from erosion. Visakhapatnam as a district is suffering from the highest erosion, and nearly 26 kilometers of its coastline has been eroded. This will be our area of interest, and let me zoom into it on Google Maps. The city, which is Andhra Pradesh's most populous and largest, is also known as Vizag. One of its landmarks is observed on your screen. It's the Vizag port, which lies roughly at the center of its coastline. Also a very popular tourist destination because of its wide variety of beaches, which we will study and which you can see on the screen. Rushikonda is one of its famous beaches, as is Ramakrishna Beach and several others. Let me show you an article involving Rushikonda Beach, just for you to gain further context. The New Indian Express had reported in this article from 2016 that the number of visitors flocking the popular beach destination of Rushikonda were declining rapidly because of the nature of the beach. And in July of that year, virtually the entire beach had been wiped out due to heavy beach erosion, spurring conservation efforts. Now, radar imagery does not appear like optical imagery, the kind of which we've used thus far. It does not look like a color photograph. Therefore, we can just glance at the topography and terrain characteristics of Vizag's coastline in order to aid our interpretation of the radar reflectance values later on. As you can observe, there is a distinct sandy, grainy texture surrounding Vizag's coastline, besides the standard features such as waves hitting the shore and so on. As a next step, we'll visit geojson.io, a platform that I've even used in my previous workflows, in order to download the area of interest coordinates in a WKT file format, a well-known text file format. I have zoomed into Visakhapatnam on the map and will draw a polygon over it and hit the save button and save it as a WKT file. This WKT file will be useful for us in a couple of junctures later on in our workflow. Let me save the downloaded file onto my working folder. This file can be opened in a notepad and it just contains the coordinates in a text format, as you can see. As a next step, let me visit Copernicus browser, a platform that we've used previously before to download the Sentinel optical imagery. This time we will use it to download the Sentinel satellite constellation's radar imagery. Now, we don't need to zoom into our area of interest. We just can upload the WKT file and it will straight away zoom into our area of interest. Subsequently, we'll go to the search button and select the Sentinel-1, which is the radar imagery. It captures information in CSAR. CSAR is meaning C-band of synthetic aperture radar. You can pause the video over here if you wish to read a fact sheet about Copernicus Sentinel-1 platform. It's when was it introduced, as well as what are its applications and users. Now, why are we using this particular workflow of radar imagery? It has certain distinct advantages over optical imagery. So optical imagery, you knew, were influenced by clouds and was impacted by weather conditions. But radar imagery, because the source of illumination is the sensor on board the satellite and not the passive illumination such as sun, when it comes to optical imagery, we can basically obtain the images even at night time and even if there is a cloud cover. So the radar rays, the C-band, basically pierces the cloud and the reflectance values are also not affected. Now, we will capture the imagery in interferometric wide swath mode, which has a resolution of 100 meters. So 1 pixel is equal to 100 meters. So this is one of the disadvantages because the resolution is not that high, but then there are certain advantages of using Sentinel-1 imagery as well, just as I had stated before. We will use level 1 ground range detected product, and in the filters box I will select interferometric wide swath as my acquisition mode and vertical transmit vertical receive plus vertical transmit horizontal receive as the polarization. Next, we'll select the time range. I am doing a temporal analysis and I intend to use radar images from 3 distinct time periods 4 years apart. So let me download the first set of radar imagery first, which is from the current year of recording 2024. I select a 15-day time period from April to May. Copernicus browser throws me 3 search results over which basically overlaps my area of interest polygon. One imagery completely overlays on top of it while the other intersects it. So I will be more interested definitely on using the former, which completely overlays my imagery, which is the second imagery from the search result. Let me go to the product info section. The imagery has been captured on 29th April of 2024. That is okay, but what I'm more interested to observe is what is the relative orbit number. Because I'm doing a temporal analysis and I wish to basically make the area of interest, you can say the radar images, consistent over the 2 other timeline which I will be downloading the product later. So if I know what is the relative orbit number, which is which cycle in which the satellite has captured this imagery, that particular number is the unique identifier which remains consistent over over the cycle of the satellite on any given day. So now let me select a different time period, which is from 2020. Now this similar timeline. One added step which we'll adopt this time is to input the relative orbit number in the filter section. I will key in 90 because that is the RON which I'll be interested in, and subsequently I'll hit the search button. There are 2 search results. One is from May, 8th May, and the other one is from 26th April. Now, unlike optical imagery where we used to observe the cloud cover, we don't need to do this for radar imagery. So I'll just click any one. I'll select any one of the product and add that particular product onto the workspace so that I can download it later. Thereafter, I'm selecting a similar time period from 2016. There is one search result which is captured on 5th May and I'm just adding it to the workspace once again. The workspace can be accessed from here and it contains all my previous history and which products I have earmarked. So these 3 products I had earmarked. I have already downloaded it onto my system previously, but this is how you basically hit the download button. These are large files. nearly 2 GB each, so it will occupy space. The zip files, as I've indicated, I had downloaded and saved it previously in my working folder. These are fairly large in size, so you need to have sufficient bandwidth on your hard drive. Let's open Sentinel applications platform, the Snap software, to post-process this raw radar imagery from the Sentinel coastline of satellites floated by European Space Agency, which are very useful for Earth observation purposes and which we'll use for delineating the shoreline. Upon clicking the bands of one of the product, this is how the imagery looks. See, it does not look like a normal photograph. It just contains the reflectance values of the radar, C-band radar, which the satellite's transponder had thrown on the Earth's surface and which the receiver on the satellite had captured the reflectances of. So there are two distinct bands. One is the amplitude and the intensity. And if I go to the pixel info tab, I can basically see what is the value over that particular pixel. And I've indicated that each pixel is basically 100 meter in resolution. So amplitude is captured in VH as well as VV polarization as I had selected, and the same applies for the intensity band. Let's begin processing the imagery, first by developing a graph using the Graph Builder tool, which will contain a set of sequential processing steps. The subset tool will be our first processing step. It will help Snap to do faster processing as it will clip the dataset to only our area of interest, thereby limiting size of the dataset considerably. Subsequently, the Apply Orbit File tool will help Snap to update the metadata of the dataset by obtaining the precise velocity and position information of the satellite when it had captured our imagery. Subsequently, the Thermal Noise Removal tool helps Snap to remove the inherent background noise of the satellite's receiver. The Calibration tool helps Snap to assign the reflectance values to the precise pixels on the map view, thereby facilitating quantitative analysis. Subsequently, the Speckle Filter tool helps Snap to remove the inherent salt and pepper texture which is present in the raw imagery dataset. And finally, the Terrain Correction tool helps convert the dataset, which is in a geographic coordinate system as standard by default, into a projected coordinate system, thereby making it usable for further processing on other GIS software. We will connect the graph, and this is the set of commands needed to convert the input into the output. However, if you face an error, just as in my case, feel free to split the graph into two distinct graphs, which will basically remove the error, and you will be able to perform the tasks also. Instead of individual processing using the Graph Builder tool, we will batch process all the three files together. So once I open the batch processing tool and add all the three files, what we will do is load our graph. I had split the graph previously already, so we will first do subset apply orbit file only. So in the subset, as you may be familiar from the previous workflow as well, we basically select the bands which we require. This time we will only require the VH polarization bands, so we will only keep that. And in the geographic coordinates, we have our WKT file which contains the precise location of our area of interest in a WKT form. So we will just update it, and as you can see, the yellow polygon indicates our area of interest. In the apply orbit file, we will just keep everything as default and also click the do not fail if orbit file is not found information. So once we have it and we determine the correct directory, we can run the tool. The tool doesn't take too long to run, depends on the system to system. So once the output is generated, I can show you what the output is, but typically it is not needed because we can run the entire processing steps in one go also, which we were unable to do this time. So the output contains the amplitude and intensity information in a VH polarization. So I'm opening all the files, and in case you want to read the pixel values or just compare it side by side, you can feel free to do so if you are doing this workflow yourself. Now let's proceed to do the second part of the graph, again using the batch processing tool itself. So now we'll have to use not all the 6 files, but only the 3 output files from the first processing step. So we'll first remove the raw imagery dataset. So we are now left with the processed files. Subsequently, let me load the graph. It will basically, we'll do thermal noise removal, calibration, speckle filter, terrain correction in this step. In thermal noise removal, we will only select the VH polarization. We don't need the VV polarization. In calibration, we will leave everything as default. The speckle filter, we will also leave everything as default. We can select the sigma naught band. In the terrain correction, there are a few steps which we need to do. First is select the band. Subsequently, instead of 3 sec, which is of a lower resolution, we will select SRTM 1 sec HGT. Next, I'll uncheck the mask out areas without elevation box. By default, masking areas without elevation would essentially mean masking out the water pixels from the dataset, thereby leaving only those pixels attributed to land. Conceptually, this is a beneficial outcome when it comes to coastal erosion. However, I have removed this step after much deliberation because I feel that the low resolution SRTM elevation dataset that SNAP uses to do the masking is from the early 2000s, and hence it is old. It does not represent the current reality very well, and I strongly suspect it leads to erroneous masking. The final step in terrain correction, what we will change is basically convert the map projection from the default geographic coordinate system of WGS84 geographic lat long to a projected coordinate system of UTM WGS84 automatic. The map projection automatically switches to zone number 44, which corresponds to our area of interest. If you remember our previous workflow using Sentinel-2 imagery, the area of interest which lied on the west coast of India fell under zone number 43. This area of interest is on the east coast and falls under zone number 44, which SNAP automatically detects and pastes it. Finally, the write command, we just have to check whether the name and directory correspond to our preferences and hit the run command. Depending on system to system and the number of imagery that you are batch processing, it will take a reasonable amount of time to do this particular step. For the inputs number 4, 5 and 6, now we have output numbers 7, 8 and 9 published by SNAP onto the Product Explorer view. This time around, there is only one single band of output which has been published, sigma naught VH band. Straight away, do you notice the similarity of this view? Have you seen it somewhere before? Let me show you. This is how the imagery looks on the optical imagery as well. Now you may wonder what's the big deal about it. By default, if you were to skip the video to a previous timeline, you will see that because how the satellite had captured the imagery was inverted and a different, you can say, angle. And now because we have applied the terrain correction, it is in the right angle as depicted on a globe, on a map view basically. Now what we are doing is on the pixel info tab, we are observing the values. Now this is a very important step because straight away you can notice that the land pixels would have a different value and the water pixels would have a different value. Now radar imagery, how it works is the water pixels are typically you can say have low reflectance value. So hence they are darker in shade, whereas land are higher in reflectance and therefore they are more whiter in shade. Now what essentially we want to do right now is to remove the black pixels completely from the dataset. Thereby we will only be left with the land pixels, and which will allow us to delineate the shoreline. So in order to identify which is the correct pixel value which corresponds to the water pixels, we'll just have to do some manual exploring. So we can see that the intensity of the dark at the absolutely jet black pixels lies anywhere between 0 to 0.005, 0.0043. So 0.005 and below is, in my assessment, where the jet black pixels are located. And any pixel value above 0.005 is, firstly, you can say, slightly in those hazy white spots, and we are currently ignoring it for the time being. And you can say pixel values of above 0.1 are corresponding to land, that we are reasonably sure about. So for this particular workflow, this particular demonstration, let's use 0.005 as our you can say threshold, which we will use to delineate. And now I would like to circle back to the point we had observed the topographical characteristics, and you can see that the semi-white, semi-black pixels correspond to that particular hazy nature of the beach, of the portion of sea adjacent to Vizag's coastline. So nevertheless, I mean, I'm not being too picky. I'm just masking out the absolutely jet black pixels by performing a new step, which is called using the band match command on the existing band. So on product number 7, which is from 2024, I'll right click it and go to band match. I'll name the product as the landmask, and I will input a expression which will basically do some quantitative analysis and which will leave out all the water pixels and leave only the land pixels. So the command which I will use is, if the value of sigma naught VH for that particular pixel is less than 0.005, then make it as NaN, which means no data value, and else make it as 1. So essentially I'm saying, if it is a water pixel, then mask out those pixels, and if it is not a water pixel, then make it bright white, thereby allowing for easier demarcation. So as you can see, the output has been generated. While this output is certainly easy on the eye and is convenient for post-processing as well, just in case you wish to test the accuracy of the applied thresholding, one can do so by using a slightly modified formula. Let me show it to you by creating a new band for comparison. I'll name it as test, and instead of the land pixels being marked with a value of 1, I'll ask Snap to keep the land pixels with the original sigma naught value which was generated in the previous output. Let me show you the new band result. What we'll be keen to observe is the edge of the coastline. If our thresholding is correct, there should not be any discernible jet black pixels. But in our case, as you can observe, there are still a few jet black pixels. Using the pixel info tab, we can observe the intensity. It is slightly higher than 0.005. So it is like 0.006, 0.0075 and so on. So in an ideal world, we have to basically modify our thresholding in order to get an appropriate result. But for this study purposes, I'm not changing it. I'll keep the threshold as the 0.005 which we had originally selected. Let me delete the test band and create a new landmask band using the same thresholding of 0.005 to keep the methodology consistent across all the 3 data products that we are using from different timelines. The output is quick to generate. Also, remember to uncheck the virtual box, because that will not save the product. By unchecking it, it will save the product. Now we are basically done the post-processing on Snap, and we'll have to export this particular output to our system so that we can further process it using ArcGIS software. We can use a different software if you like also, but I prefer using ArcGIS. The way to export the product is by either going to File and Export and exporting it as a GeoTIFF, which is basically a geolocated image file, or you can right click on the image view and click on Save as Image, click on Full Scene and Full Resolution, name it as you like and save it as GeoTIFF and hit the Save button. So we've done so for product number 7, which if you observe is from 2024. We will replicate the same step for products from 2020 and 2016 as well. Meanwhile, in case you are wondering what are those black pixels on the white land and the white pixels on the dark sea, those are basically certain water bodies, small water bodies on the land, as well as tiny, objects on the sea. I think that's the only possible reason why it is, or maybe it could be a certain noise and backscatter as well, but I think it is more likely the former. Now, we have saved all the 3 output files as GeoTIFF, and we will proceed to basically do the next steps on ArcGIS Pro. Let me drag and drop the 3 products onto the map view on the contents pane of ArcGIS Pro. All the 3 products have been loaded. I'll just choose to minimize the expanded view as I do not want extra information on my eye line. One thing which I missed informing you is that while we had used the website geojson.io to download the WKT file format for our area of interest, we can do the same step from within Snap itself. All we need to do is draw a polygon over the area of interest and right click on it to obtain the WKT from geometry. We can copy and paste it in our text file to use it for further, processing steps as well. Also, while we had proceeded without masking the water pixels by using the SRTM elevation band, let me show you how it works and what is the result like. We'll go to raster and go to masks and select the land sea mask function. Within that, we'll select the product which we want to basically apply this command on. Ensure that the directory is correct where we want to save it. Select on the source band. So we want to use the land mask band where we did not use the elevation earlier, but we are now using it. We'll select mask out the sea and use the SRTM3 set digital elevation model to perform the masking out of the water pixels. Let's see what the output looks like. Just to let you know, a digital elevation model is basically bare earth, elevation model. So it does not capture the height of the features on top of the earth, let's say a tree or a building or something like that. It only captures the height of the bare, ground features, bare earth features, that is. So this is the output which has been generated after performing the masking by the SRTM model. So you can see the white pixels over the water body has been completely eliminated because those were part of the no elevation, data set which was obtained by SRTM mission. Coming back to ArcGIS Pro, once again, we are now ready to perform the next processing steps. And as I had indicated to you before, you do not need to worry about those white pixels which you see on top of the sea. We will remove it in one of our next steps as well. So the first geoprocessing tool which we will use on ArcGIS Pro is the raster to polygon command. This is something which we had used in our previous workflow involving Sentinel to imagery post-processing as well. All we are doing is converting the individual pixels into a polygon shape. So from a raster to a vector file is what we are doing via this geoprocessing tool. We have performed this tool for 2024 product. We will repeat it for 2020 and 2016 product as well. As you can see, upon clicking on it, there are distinct shapes which are being selected instead of individual pixel values. Upon opening the attribute table, you can see that there are 1339 distinct shapes in the particular area of interest. Now that is large because of the several small tiny pixels on land and tiny pixels on sea. The figure of the number of, objects is high because of that. But otherwise, the two main objects are, the one with the largest shape area, and we will choose to preserve one of them in one of our next processing steps. Our next task is to isolate the appropriate polygon shape which contains the shoreline in its entirety from the polygon layer, and further convert this particular shape into a polyline layer, which would allow us to isolate Vizag shoreline. However, we are unable to run that tool which we typically use, the polygon to line layer, right now because our current polygon shape is too complex and comprises of multiple attached and overlapping shapes. Instead, we will use an intermediary step, feature outline mask. We'll select our input layer and set an appropriate reference scale, in our case 1:100,000, and set an appropriate coordinate system and run this particular tool. So what this tool essentially does is it creates a simplified polygon outline layer, and the result can be evident once we explore the attribute table. So once we click on the polygon, you can see the pop-ups. We are able to see that visualize the particular polygon which we would like to extract. So it can be separated in its entirety now. And upon exploring the attribute table, you can also observe that when previously we had nearly 9,000 shapes, right now after running this tool, we just have 1,661 shapes. And obviously the second, the second shape is the important to us as it comprises of our shoreline, and we can basically isolate it from this particular list. How we do that? We press Ctrl Alt. We just leave the second object ID and which contains our polygon of our choice and delete everything else and hit the save button from the edit tab. So we have isolated the polygon of our choice. Similarly, we will repeat this step for the other two layers, 2020 and 2016, that is. The margin of the outline, we keep it as a very low figure, which is 1 millimeter. So essentially, we are not tampering with the layers properties, just we are creating a simplified outline. Once again, the second largest feature contains the polygon of our choice, because we can see the shoreline of Vizag from it. So we'll keep that, hit save using the edit tab. Finally, for 2016, we will repeat the same process. And hit the run button. In the attribute, there are just 850 attributes, and once again we'll sort it as per the descending shape area. The second row is of importance. We'll keep it, delete everything else, hit the save button. So now we have the polygon of our choice for all the three timeline of our study. And instead of a filled color symbology, we will change it into a outline, because they are actually outline of the, you can say, area of interest. We will also color it in a different color so as to basically distinguish from one another. There are a variety of shapes, sizes, dimensions, colors, thickness we can basically play around with to obtain the preferred, you can say, symbology of the layer. Now then, we've completed playing around with the symbology, and frankly speaking, this is not very important for our workflow. Just for visualization purposes, I have done this step. Our next step is though very important. We are now in a position to use the tool which we could have used earlier, but we are using it now, polygon to line command. This will basically break down the polygon layer into polylines, and we will further extract the shoreline from this particular generated output. Let me repeat this geoprocessing tool over the remaining two input layers from different timelines. We can choose to name the output files as per our choice. By default, it saves in the project's geodatabase. So the new output has been generated, but you will not be able to spot, because they look, quite frankly, same as the previous output. But then once I switch off the older outputs, you can see that the new shoreline has been generated, and these are individual lines. And if I zoom out and if I click on that particular line, the entire shoreline is being basically selected. Now it's not necessary that the entire shoreline can be selected. Maybe some of the times it breaks down into multiple shorelines, but in our case we are fortunate that the polygon basically houses the entire shoreline. Once again, we don't want the other outlines, we just want to preserve the shoreline. So we'll just select that particular, once we use the descending order on the shape line, we find that there are certain simplified, you can say, polylines which we do not want to keep. So we are only interested to keep the largest polyline, which is basically the outline of the entire area of interest. So we'll just keep it and delete everything else. That is one option what we can do. But what we will do instead is not complicate the procedure that much. We will just directly use the split tool. So once we select the largest, you can say, polyline from within that layer, we will use the split command and create two crosses across the area which we want to cut off from the main shape. So now the shoreline is highlighted because we have cut it off from its two ends. Once we go to the attribute table, you can see that the shoreline shape has been extracted. We can just click on that particular row and see. So the largest shape of the line is of the other outline, but the second largest one corresponds to our shoreline. So we'll delete everything else and just preserve the second largest polyline, which we have artificially, you can say, cut off from the main shape. We've saved this and our new shoreline has been generated. So this is the output that we were craving for when we had initiated our study. So let's examine it. Is the shoreline accurate? I'll say it is reasonably accurate. Remember that our thresholding was slightly off the mark. So keeping that in mind, if we would have put an appropriate thresholding, maybe the shoreline would have been very, very accurate. Right now, it basically mimics the shape of the shoreline, but it is located at a certain distance away from it. But it's sufficient for you to know that this method works, and this is how the output looks. So now that we are familiar with what the processing steps are, we'll repeat it for 2020 and 2024 layer as well, very quickly. Sort the shape length column in descending order. We want to preserve the largest shape, so we'll select it and we will split it so that we will cut off the unnecessary ends and just keep the shoreline as a separate row, which we will isolate and delete all the remaining features. Remember to keep saving your file from time to time. And even when you make edits, you don't have to save the project, you have to save it from the Edit tab. So we've created the new shoreline. We've extracted the shoreline, that is, from 2020, and we'll now do it for 2016. In case I am speaking too fast, you can play around with the YouTube's play speed and reduce the play speed so as to make the content much more easily audible for you. In any case, the subtitles are there for you to basically have a guide for the workflow. Right then, we are done with creating all the three shorelines. The thing is, we are not able to very clearly spot them. So again, we can modify the symbology so as to demarcate one shoreline from the other, and then we will try to interpret what the results are. So 2016 layer, we'll color it as green. So the oldest timeline is green, the middle timeline is yellow, and the newest timeline is red. In this way, it would be easier for us to interpret. Now let's navigate around the coastline and see how the output has come out and what we can basically interpret from it. Remember that we are just creating a visualization. So initially we did it in a, you can say, visual manner. Right now we have created a shoreline using Sentinel 2 first and now on Sentinel 1. And in our subsequent workflow, we will also measure the net change in the coastline. So in case you are wondering, that comes next. So there is an evolution of that. Now I have blanked out the 2020. So I'm currently only comparing 2016 with 2024. Around the edge, the green line, which is 2016, is closer to the beach. So what it essentially shows that there is accretion on this particular side, although in some areas there is erosion. Actually, what happens is wherever there is urban infrastructure which is created near or within the sea, there is a updrift, downdrift, which basically impacts. So typically wherever there is a port, there are certain areas on, let's say, downdrift would face accretion and certain areas on the upstream will face the erosion. So on the northern end of the port, you can see that there was a significant erosion. But on the southern end of the port, the beaches which are located south to it, there was reasonable, you can say, accretion. remember that the news articles which I had showed to you initially at the beginning of this particular, you can say, subset of video, those were referring to the timeline around 2016. So subsequently there has been change, and as you would have known that there were certain conservation efforts too, which could be the reason behind accretion. This was how Rishikonda Beach was, and as you can see, the news article was published in 2016. But subsequent to that, there is a certain, you can say, accretion around that particular beach. So just FYI, the erosion and accretion are just natural phenomenon, but the rate of erosion and accretion is something to worry about. So erosion by itself is not a negative aspect, and it can be restored, and it's a natural phenomenon. Meanwhile, let me show you, while we have you can say automatically created a shoreline, there is also a way to manually create a shoreline. Now, depending on case to case, you may choose whether to use the automatic way or manual way. So in the manual way, you just have to create a new feature class from the catalog pane. You have to right click on the geo database and create a new feature class, and subsequently you add a line on top of the edges of the white pixels. This would kind of give you a representation of the coastline. Now obviously, because our area of interest is too large, this is not an appropriate step. However, if you want to basically observe, you can say with more accuracy, I can't say more accuracy, but in a more detailed manner, a particular beach, then perhaps this way would be suitable for performing that kind of analysis. Also, while we have used SRTM dataset and it has a resolution of 30 meters, I just wanted to let you know that there is also ALOS Pulsar, which is captured at a later date, 2011 onwards, and that is of a reasonably higher resolution. You can get it from this website, search.asf.alaska.edu. You have to create a login account and create a polygon and search for the DEM layer. The high-res dataset is of 12.5 meters resolution, which is significantly better than that of SRTM. However, we are unable to use it in Snap directly, although we can use it in ArcGIS Pro to basically mask out the water pixels. So as you can see that 2006 to 2011. So it is relatively newer, and obviously newer than SRTM. So this is another aspect which, before closing down this section of the video, I wanted to bring to your attention. This ALOS Pulsar is by NASA Earth Data. I hope you like this demonstration, and apologies if I have made any errors in communication. Thank you. Let me switch to the default view on ArcGIS Pro, which is the topographic base map. In this article published by the Times of India in December 2023, it states that National Center for Sustainable Coastal Management found 21 out of 41 surveyed beaches in Goa to be experiencing primarily sand erosion, but in some beaches even accretion as well. So these are, you can say, prime candidates to study shoreline movements of what we are about to do. While the study was conducted for a period between 1990 to 2018, we will be focusing on a different timeline. But our area of interest, just to specify, is one particular beach of Goa, which is Anjuna beach, which is experiencing both erosion as well as accretion. To give the context of the location first, let's go to Google Maps and search for Goa. It's a tiny little state on the western coast of India. This is its location. It is bifurcated into two major territories, which is North Goa and South Goa. Anjuna beach lies on, you can say, the central to southern section of North Goa. Let's zoom into our area of interest. This is where it lies. Now for the shoreline delineation process which we'll be doing, we'll need you can say the area of interest in a particular file format, which is the WKT file format, or the well-known text format, which is you can say a reference to store the geometric and spatial information in a text format. So we'll go to geojson.io, an online tool where we can get this particular file format. There are other available methods also, but I find this to be convenient and easy to use. What we'll do is just draw a polygon around our area of interest. It is basically Anjuna beach and its surroundings. And then underneath the save button, we can just click on download WKT and it will download that particular file. We'll name it accordingly and save it in our primary work folder. Right, so we have saved this, and now let's go to EO browser once again, because just to see how that particular satellite imagery over that area of interest looks like. So we'll select Sentinel 2, and once again the atmospherically corrected product, and in the cloud coverage we'll keep it to a low amount. And in the timeline, we'll select a particular timeline of concern, which is, let's say, January to the April 2024. And we'll hit the search button. There are 3 search results. Let's click on one of them. As you may already be familiar, EO browser is a handy online tool to visualize satellite imagery. By default, the commonly used band combinations are already outlined. So true color is the optical photograph. False color is basically highlights the urban features very well. So it is mentioned that it's based on bands 8, 4 and 3. We've already used the NDWI, which is the water index previously. It is based on the band B3 minus B8 divided by B3 plus B8. Now, some of you may be wanting to know more, understand better what are these bands all about. So, Sentinel-2 is a multi-spectral satellite, and it captures, you can say, reflectances of sunlight in variety of, you can say, spectrum. So, not only visible light, but also the near infrared as well as shortwave infrared also. So, there are 13 different bands which are captured, and each has resolution of either 10, 20 or 60 meter. And the description are also mentioned, what basically captures what. Now the beauty about multispectral satellite is, by altering and playing around with certain band combinations, researchers have identified ways of delineating surface features. So we can use it to have an optical imagery, we can create a false color imagery. Shortwave infrared basically highlights dense vegetation as well as bare soil. Geological attributes, bathymetric attributes. So researchers have found how to basically play around with those bands to identify the surface features. So on EO browser, we also have the possibility to input our own band combination, which we determine as appropriate. So let's, for example, just use the shortwave infrared which we saw on gisgeography.com. As you can see, dense vegetation is dark green and bare soil is brown. NDWI is also something which we can explore, and it's an index formula. It's not a composite formula. Index is, there is addition, subtraction, etc. So we B3 minus B8, B3 plus B8. So it is green band minus near infrared band divided by green band plus near infrared band. So once we do that, the water features are highlighted currently in the gray shade, although we can alter the symbology to make it blue as well. Right. So there are several ways of delineating water features. So while we've used NDWI, there are several other methods also. But just to understand why we are able to do so is because water has a very starkly contrasting reflectance property than, let's say, soil or green vegetation, as you can see in this image. So in the visible spectrum, it has a low reflectance and then it basically goes blank. Whereas the others, soil, green vegetation, has relatively higher reflectances and it's basically stable across the visible and the near infrared spectrum. So this property basically magnifies, amplifies by using this particular formula. MNDWI is a modified formula which basically takes into account any reflectance from built up areas which hampers the water reading. So it's a revised formula, but then it is you can say slightly more effective than a NDWI in certain situations also. Modified MNDWI, that is. So now, I mean, the idea behind showing you this was, while its EO browser is a useful tool in terms of visualizing and obtaining and context, we actually, for this particular example, we need to delineate the shoreline. So EO browser is not sufficient for this. So we are going to Copernicus browser, browser.dataspace.copernicus.eu. This is where you can download Sentinel imagery for free, and you just you can create an account and then search for the particular area of interest. Once you are on that interest, the filters are the same. You specify which imagery you want from the Sentinel sources, as well as the cloud cover and so on, timeline. And once you do that, the search results will appear just as it appeared in the you can see EO browser. So we'll use the same timeline once again. Our cloud cover is 1%, because the lesser the cloud cover, the better it is to analyze the optical multispectral imagery. There are 7 results in the time period. Now, each of the products which are listed over here, it contains the date. So 2024, 04 means April, 23 means the date. And there is also time information subsequently in the product name. When we click on the product info, we'll get additional useful information, but I'm not explaining that, besides one particular factor, which is cloud cover. So the cloud cover in this particular product is 0.06%, which is very less. But then we are seeing, okay, is there something better which matches our timeline preference? So this one has again the same 0.06%. Now, if we were to see this particular product, which is from the 14th of January 2024, the cloud cover in this is really very less, like bordering, nearing 0. So 0.0007. So this seems like a good product for us. So we'll hit the download button, and it straight away begins downloading. It's a slightly, you can say, large file, 1 GB file. And once it is downloaded, we can basically use it. I've already downloaded it before, so I'm not, downloading it once again. Now this was 2024, and as I have already told you sometime previously, is that for the India region from 2017, the L2A, which is the cloud corrected products, which has upper atmospheric reflectances, are available. So for the same time period, as in January, we are not factoring tides and all of that, but then for the same time period in January of 2017, we have one product, and luckily for us, it has also a very good cloud cover percentage, favorable one, and we hit the download button. It's a very smooth, easy process. There was a older version of Copernicus browser before, which was again very easy to use, but the new one is much better. So I've already downloaded it before, and the files are saved in my working folder. For the next step, we will use the SNAP tool. SNAP stands for Sentinel Application Platform. It is a handy tool for not only visualizing satellite imagery, but also processing it. It has been developed by European Space Agency, the same organization which operates the Sentinel satellite constellation. I've downloaded the latest version, version 10. And for this particular workflow, just the Sentinel toolbox version of the software is sufficient. You can download it as per the operating system which you are using. Once we've opened SNAP, we will load the downloaded satellite imagery onto the Product Explorer section. I click on File and Open, and go to my working folder and click on the zipped file which I had downloaded. There's no need to extract the contents of the zip file. Snap reader can directly read it from the contents from the zip file itself. As you can see, the product of 2024 has already been loaded. We'll load the product of 2017 as well. Instead of using the same file open command, we can even use the drag and drop feature to load the other product onto the software. Now both have been loaded. Let's explore. While there is a ton of information, we will predominantly be using the bands folder. In the bands folder, you can see Sentinel-2, which I've already specified, contains 13 bands. All of them are listed. So let's visualize the B1 band, which is the ultra blue band. Now the output isn't ultra blue in color, but it basically carries the reflectances of the sunlight in the ultraviolet or ultra blue spectrum. Besides, it has other spectrum as well, like with visible light as well as infrared. Now, so one can see how in each of the individual bands, how the product looks like. Each pixel view in the image has a particular reflectance value associated with it. And as I hover the cursor, you can see that particular value underneath the band section of the Pixel Info tab. Now, just as in EO browser, we can visualize the imagery in some of the popular band combinations. So, clicking on Window and open RGB view, we can select the MSI natural color profile, which basically inputs B4, B3 and B2 in the red, green and blue channels respectively. And the output is spectacular. It is basically the optical imager for natural photograph of the satellite imagery. Now that I have taken you through the basics of visualization of Sentinel-2 imagery, we'll move to the more important aspect, which is the processing or the analysis aspect of the imagery. Now, here we will use the Graph Builder tool. By going to the Tool tab, we'll just select Graph Builder and we'll build a graph which would contain all the processing steps. Now, I will not take you through all the processing steps in detail. I'll give you a short, you can say, introduction. But then I have already written an article on this exact workflow, which is mapping water bodies using optical and radar satellite imagery. The first half of this article would be useful for you in case you want to basically understand all the processing steps in detail. You just need to search for this particular article on my website mapmyops.com to do so. So let me take you through the processing steps. It is possible for us to do each of these processing steps one by one, but then it would be too time consuming for me to show you that. There are 5 processing commands which we will add in the graph, beginning with resample, then with subset, followed by 2 boxes for band math, and finally the reprojection command. You can follow my mouse movements to know how I am accessing those commands. Once we've listed all these commands onto the graph, we'll just right click and select the connect graph button so that the order of processing is specified by us to the software. So a red arrow will link all the commands in a single graph. Underneath, we will highlight the options which we are gonna select for each of the command from the variables. So read is basically which product we are gonna process. The write is how the final product should be named. Resampling for Sentinel-2 imagery is a must because each of the band, as you already aware, are of different varying resolutions. So what this does is, by using an algorithm, it basically levels the playing field and makes all the bands with a same resolution. So our resolution which we are targeting is of 10 meters, which is the B2 resolution. So we'll select that particular option and leave the rest as default. Subset is because each imagery is 1 GB and processing it is time consuming entirely, and there's no need for doing so also because we are just interested for a particular section within the entire, you can say, satellite imagery. We are only focused on the Anjuna beach. So our WKT file format, which we had downloaded, contains that coordinates of our area of interest. So we'll just enter it in the WKT section and hit on update. So as you can see, the red outline is of our Sentinel-2 imagery, whereas the yellow small outline is of our Anjuna beach, which the polygon which we had downloaded using the WKT format. The next command in the graph is bandmaths. Over here, we will input a formula to delineate water features from other surface features. There are several water radiometric indices to choose from. We will utilize MNDWI because it is slightly better than NDWI as it eliminates background noise. We can straight away paste the formula into the expression section. The next processing command is bandmatch2. We will rename the target band this time to CMask because this is essentially what we are gonna make. The output from the previous command bandmatch, which is the MNDWI output, will range pixel values from -1 to 1. And typically water features are between 0 and 1. So this is a binary formula where we are specifying the software that if a pixel value in the previous output is above 0, then you make the pixel value as 1, and if it is below 0, then you make the pixel value as 0. So the output of this particular command will either be a pixel value of 0 or 1, which basically delineates. So if it's a 1, then we can assume it's a water feature, and if it's a 0, then we can assume it is a land feature. So this mask is important because it kind of simplifies the entire workflow. Once we've done inputting the formula by editing the expression, we can go to the reproject command. We will transform the output from a geographic coordinate system GCS to a projected coordinate system PCS. Currently WGS 84 is our GCS. We will transform it to UTM, which is our PCS. The reason behind transformation is because to display geographic information accurately on a flat screen, PCS is required. UTM zone 43 has been automatically detected by the software because that is where much of Western India, which is our area of interest, lies in the UTM, you can say, zone bifurcation. We will save our graph as CMask because that is what our final output is. We could have straight away run the graph then and there, but then I choose to close it and load the graph and then run it. Because you cannot straight away run it, you still need to verify whether all the input, output and the processing parameters are as you hope it should be. So the read is the correct product, which is the 2017 product. In the resample, we need to change because once again we need to select B2 because that is what the 10 meter resolution we want to basically normalize our entire product to. The subset command, everything is as default, we don't need to change. The bandmatch number 1 is the MNDWI command, that is also as we had desired. Bandmatch number 2 is our binary command, which basically says either 0 or 1 should be our pixel value. In reprojection, it's a software glitch basically. We need to, once again make that change from the projection of GCS, WGS 84 to UTM. Once we are done doing so, everything is okay and we are now in a position to run the command. But before that, obviously we'll need to rename our product if we choose to do so and see whether the directory is the correct one where we want to save our product. We are naming the output as 2017 January, Anjuna Beach. The graph is very quick to run, although from system to system the processing speed times will differ. We can also use the batch processing command to process both the products together. But then I wish to basically show you one by one and not make it overly complicated for you, although it's frankly speaking not very difficult to run the batch processing tool also because all the processing steps remain one and the same. Once again, we'll check all the parameters are as per our desire and then we'll hit the run button. One thing you may have observed is in the band match section, we had named our band output as new band, which is the default only. There was one reason behind not naming it as MNDWI because the software was taking it as a glitch because band match 2 was dependent on it. Nonetheless, we'll rename the output once again for the second product, which is 2024 Jan, and run it. both the output are now displayed on the Product Explorer section. Let's examine the output. Once again, we'll go to the bands folder. There's a ton of bands. I don't know how it was generated, but we had only asked the graph to generate a sea mask, and luckily that has been generated. So the sea mask is very clear. It is basically detecting water bodies. You can see that the shape of the sea mask is exactly over our area of interest. So it has matched up as per the subsetted the image as per the polygon. And all the water bodies which it has identified are white in color, and you can see the pixel value. If once I hover on the screen, it is 1. So that is what we had asked the bandmaps column to do, the second one that is. And all the other features barring C are all black in color. So because the location of our file is such, much of the white mask is all of the sea, and there are very tiny spots which are on land, water features. Because we don't need the other, noise, other bands which were randomly generated, we'll just delete it and save the product once again. We'll open the second product also. You can see it is one and the same. Once again, we can remove all the other bands which are not important to us and just keep the sea mask band. Just to ensure that the product is updated, we will hit save button to both the outputs. Going to our working folder, I just wanted to show you that while the raw file was 1 GB nearly, the processed files are very small in size, like a few KBs only. Totally 962 KBs. So after running the graph, we have basically just extracted the information that we need, and it is very small in size, predominantly because we had used the subset command. Finally, we will now utilize another software for further processing, and for that we need to save it in a particular file format. So we'll click on the product which we want to extract, go to file, hit on export and save it as a GeoTIFF BigTIFF format. The name of the file is the same as the name of the product, and that's okay. This was the workflow on Snap tool. Now this same workflow can be utilized on other paid GIS tools, but I find Snap, because it is free and it's very easy to use, I find it a very good medium, and it's for any remote sensing enthusiast, it's a very nice software to learn. Our next step can be done on ArcGIS Pro. It's a paid software, but luckily they have a 21-day free trial. And for certain other, processing steps, I prefer using Esri's ArcGIS Pro. Esri's GIS software is the best out there in the market, and they are kind enough to offer a 21-day free trial of their most advanced spatial processing tool, ArcGIS Pro. The processing steps of installing, I am not showing it in this workflow. It's a large file, and you just have to, hit the executable file and run it. Currently, I've already loaded it and I'm running the software. We can create a new project, but then I've already created one by the name of Goa Shoreline. Because I had tested the workflow earlier, you are greeted to a satellite imagery base map zoomed into Anjuna beach and its surroundings. By default, you will see your software's country of registration zoomed in a topographic base map. I have dragged and dropped both the output GeoTIFF files which we had exported using Snap onto the content pane of ArcGIS Pro. It is visualized in the map view as well now. Before we proceed further, I wanted to show you an interesting anomaly. When I switch to the topographic map base map, which is the default base map, and which just looks like any political physical map of a country, while the location appears to be the same, as in it is our output layer is superimposed on the correct spot, which is Anjuna beach and its surroundings. But then the superimposition is not pretty accurate, and you will get to see what I mean momentarily, when I play around with the transparency of our output layer. You see some areas which should have been marked as land pixel are appearing as water pixel in our output and vice versa. I felt it was some processing error on my part. Perhaps both the base maps had a different coordinate system also, but none of these two hypotheses of mine were accurate. The accurate reason, in my opinion, is a subtle difference between what a coastline is and what a shoreline is. The imagery shows a standard view which depicts a shoreline, but a country's coastline is something different. To know more, read my article, the introductory section of it, which is devoted to this particular aspect. The link is mentioned in the description. When we click on any portion of our output, a pop-up appears which contains the information. So the pixel value, which is either 1 or no data value, or which is 0, is appearing. That was how we had saved the output in Snap. Our first processing step on ArcGIS Pro is to use the INT tool. It basically converts the output of a layer into an integer format. Now, you may be wondering, just as I did, our output from Snap is in an integer format. So why is the need to run this tool? I think it's some sort of an anomaly because the layer is not treated as an integer format. It is treated as a floating layer. So we need to use the INT tool once again. And the benefit of this tool is it removes all the no data values. So what you are seeing right now, the newly generated INT layer, is containing only the water pixels, and not the land pixels have all been removed from the raster layer. Let me use the symbology tool. It allows a user to alter the appearance of a layer. I'm using this tool in order to change the color of 2017 layer, which would allow me to get a visual cue of how the shoreline has evolved over a period of time. Observe the edge of the coast closely. You'll see dark blue pixels. These are actually the spots which have undergone erosion from 2017 to 2024. Our next step is to use the raster to polygon tool. Raster is a conglomeration of thousands of pixels. Currently, in our layer, all the pixels have a value of 1, which denote water pixels, and we no longer need that information. We just need the exact, you can say, shape or the location of the water body, which will help us in our subsequent workflow of delineating the shoreline. So this particular tool converts the raster layer into a polygon shape, which is a form of a vector layer. I'm keeping the simplify polygons and create multi-part features option selected because it is suitable for our particular workflow. Both the layer outputs have been generated. I'm choosing to symbolize it in a different way rather than having colored fills. I'm just choosing to keep an outline of the shape because the entire layer no longer comprises pixel values. It's just a singular shape. So if I click on any portion of the shape, you will just see one attribute which contains the length and area of that particular shape. Even in the attribute table, you can see the length and area, and one attribute is mentioned. This is the utility of this particular tool. Now that we have converted our layer into a vector format and into a polygon, we'll proceed to the next step, which is to convert the polygon shape into individual lines, and then we'll subsequently extract the shoreline adjacent to Anjuna beach. We'll enter the input layer and the name of the output layer. It's a very simple tool to run. Likewise, we'll replicate it for 2024 layer. Using the symbology tool, we'll just alter the color of 2017 into a dark red shade. So this is the new layer which contains lines. So when I click on the layer, it will not select the entire shape. It will just select a bunch of contiguous points, or you can say individual lines. So the line which has been selected on your screen right now is actually the line, the shoreline adjacent to Anjuna beach, and this is what we are interested to keep. So we need to extract this particular line from the generated layer. In the attribute table, our selection is demarcated. It is row number 39 and we'll need to keep this particular row. Observe that it has a shape length of 5.6 kilometers. So intuitively what we want to do right now is remove all the other rows and just keep row number 39. That is what we are going to do. We are left with just one row and we'll hit the save button, not the save project file, but under the edit tab there's a separate save button. We'll have to click on that so as to save the edit to the attribute table that we have made. And now the layer does not comprise of multiple lines, just one line. Switching over to the 2024 view, you can see that it's not the exact replica of 2017. Now the current selection selects not just one line on the coast side of it, but even on the sea side of it. So it's basically a series of contiguous points. So we need to manually attach a break line in order to delineate the shoreline which we want. So how do we go about doing so? So first let me open the attribute table. You can see that there is one large line which corresponds to our selection, which is 14 kilometers in length, and we don't want that entire line. So the way to create that manual break is by using the split command in ArcGIS Pro. Under the edit section, you can go to the split command, and all what you need to do is manually crisscross that section which you want to keep. So it will break that particular section of line away from the main shape. Observe that there was a blink on the screen at the area where we wanted to keep the break. Observe it once again as I am entering a break line. Yes. So now what has happened is it has delineated that particular shape from the entire shape. So once we go to the attribute table right now, we'll be able to see that the new shapes or new lines have been created. So instead of that 14 kilometer line, we now have 2 kilometer line, 8 kilometer line, and so on. So right now we just have to select the line which we want to keep. There are two lines which we want to keep, and we'll have to observe what is the length of that. Intuitively, we'll go to the attribute table, and what we'll essentially do is just keep those rows and remove all the remaining rows. The largest line still corresponds to the seaward facing boundary of the satellite imagery. We don't want to keep that, but the remaining line we will, the next two lines we will keep. Once again, we will click on the save button in order to save the changes we made on the attribute table, and this save is under the edit tab. Now the objective which we had is finally achieved. We have identified the shoreline in 2017 and 2024 respectively. We've done several processing steps across spanning couple of softwares, and the output is there for us to see and explore. It gives us an indication where accretion has happened and where erosion has happened. So 2024 is yellow colored and 2017 is red colored. So where the yellow color is facing more towards the land, it essentially means that the area has undergone accretion, as in new land has been added. New, you can say, sand has been added, and we can even use the measure tool to get a rough area of where erosion, what is the, you can say, the length of the erosion or the accretion which has occurred, and even the area. So such basic calculations one can do. This is a rudimentary way. I mean, this particular extracted shoreline we can subsequently use in more advanced workflows, which we'll see in one of the later example. But then right now what you are essentially seeing is how the exact shoreline has evolved, and this is not a foolproof technique. There are certain drawbacks of it, but it's a good you can say way of doing this is the first time actually where we have extracted a coastline, a shoreline basically. There's one more aspect which I wanted to show to you in EO browser, and this is useful. So if you remember, in Snap we had made a binary function that if above 0, then make it 1, which is a water pixel, and below 0, then make it 0, which is a land pixel. Now, the way 0 was identified is by, years of research by, scientists and researchers who had identified that using MNDWI or NDWI function, 0 is, you can say, the threshold where the land basically differs from sea. But that's not always the case. It's basically an approximation. So what happens, what I'm doing right now is basically saving the views. You can see right now the true color composite of the view is being depicted. Now what I'm doing is I'm adding that particular view to a compare cart, and similarly the NDWI view of that particular location, I'm just adding it to the compare cart. So we've added two layers. One is the true color layer and one is the NDWI layer. Now let's create a modified NDWI layer, which is B3 minus B11 divided by B3 plus B11. And we will save this particular visualization also as our third layer in the compare cart. We've altered the symbology. So the blue areas are the areas which are water body. Now the reason behind showing you this particular, you can say, feature, it's a very useful feature. So what you can do is, while in this particular case it's not very, very evident, but then you can see among the two layers. Let's say you want to choose between NDWI and MNDWI. You can see which of these layers correspond accurately to the coastline. That is what you can basically see. Besides that, if you can also modify the threshold. So let's say you want to, instead of 0 as a threshold between land and sea, you want to keep a different threshold, let's say a higher threshold, 0.1, and to see how it basically, whether it mirrors the border appropriately or not. You can actually do that, make that change, and the correct way of doing so is using the histogram function also. So let me show you the histogram function right now. So you can see there are two peaks. So there are two distinct peaks. The negative peak is for the land and for the positive peak is for the water body. And you can see where the break is and then determine which pixel value should be the right threshold. And you can use that as a, you can say in the formula in Snap, you can use that particular value instead of a pure 0 in order to make the correct approximation of the shoreline. Once again, this particular thresholding feature is more suitable for detecting, minor water bodies and not for, big seas and oceans. But then certainly it is a useful aspect for you to know, and it could prove decisive in selecting the right water radiometric index as well. So I hope you enjoyed this example of extracting a shoreline by utilizing Sentinel-2 imagery. We've used the Snap tool as well as the ArcGIS Pro in order to do so. A couple of workflows ago, we had derived the shoreline using Sentinel-2 optical satellite imagery over Anjuna beach and its surroundings in Goa, the state on the western coast of India, for the period of 2017 and 2024 respectively. This time around, we will be using another source of imagery, the Landsat 8. It also supplies optical imagery and revisits an area of interest every 16-day cycle. On board the Landsat 8 are two instruments, the Operational Land Imager or OLI, which captures reflectances across 9 spectral bands in the visible and the near visible spectrum, primarily at a 30-meter resolution per pixel. Also, it contains a thermal infrared sensor which captures temperature-related information using 2 spectral bands. So how does the Landsat 8, which is operated by USA, fare against the Sentinel-2, which is operated by European Union? One can say, as you can see in the image, they have a similar spectral profile. if you ignore the thermal sensor, which the Sentinel-2 satellite doesn't have. In terms of resolution, Sentinel-2 captures information at 10-meter resolution, 20-meter resolution, as well as 60-meter resolution. Primarily, you can say at a 20-meter resolution. So when it comes to the pixel size, it is basically Sentinel-2 has the slightly upper hand, relatively, that is. Also, in terms of the revisit time, its cycle is 10 days, which is better than Landsat 8's 16-day cycle. So Landsat 8 imagery can be sourced from a variety of sources. I prefer to use Earth Explorer website managed by United States Geological Survey. To begin with, one can either choose to upload a shapefile of our area of interest, or as in our case, we'll just type in the landmark, which is Anjuna Beach, in the geocoder section, and Earth Explorer shall figure out the precise coordinates, as well as update the view of the display, which also serves as a filter. It will only show us search results which overlap this particular pin. When it comes to timeline, let's maintain consistency. Because we had downloaded Sentinel-2 imagery from 2024 in the month of January, we'll try to basically figure out Landsat 8 imagery from that particular timeline itself. Let me key in the timeline. I'll key in from Jan to March of 2024. One can also select cloud cover. In optical imagery, we need to ensure that it has a very low cloud cover. So we'll just limit it to maximum of 1%. Besides that, one can tweak with the result options, as in how many output you want in a result view. Coming to the important aspect, we'll just select which satellite imagery we want. We want the level 2 Landsat collection. Level 2 basically captures surface reflectances. Landsat 7 was discontinued in January 19, so before that the data is still available, but Landsat 8 or 9 is what is precisely suitable for us. Landsat 9 is relatively new, 2021. So upon clicking Landsat 8 or 9 level 2 product, we find that there are 7 search results. Similar to the Sentinel satellite imagery, the information is present on the screen like it was present in the Copernicus browser. We can access the metadata, observe the orbit, observe the cloud cover, and determine which product could be of use to us. This particular product has a 0% cloud cover. Now, because we are interested in January, one can see that there is a product from 11th of January in 2024. And upon observing it, it also has a very low cloud cover. In fact, it is 0. So this is a suitable imagery dataset, and one can click on the download button. The benefit of downloading Landsat imagery is one doesn't need to download the entire file. One can be selective also which bands one wants. So for shoreline delineation purposes, we need bands 2nd to 7th. So 2, 3, 4, 5, 6 and 7. Straight away it downloads the, upon clicking the download button, it downloads the bands. Each of them are basically around 60 to 70 MB in size each. Now the method of shoreline delineation is the NDVI plus Tasseled Cap. So for that, we will do the study on ArcGIS Pro, and there is a particular toolbox which we need to download. The URL is mentioned on the screen. One can even Google search. So upon clicking the downloaded zip file, we will use the 10.1 to 10.2 tool. So we'll just only extract that particular tool because the others are not working. I had tested it. We'll save it in our working folder. By that time, the bands also have been downloaded. This is the entire workflow we've completed from downloading the Landsat 8 imagery, and we will now begin the processing aspect on ArcGIS Pro, beginning from clipping the raster to NDVI to a number of steps before creating the ultimate shoreline boundary from Landsat 8 imagery. if you remember, in Sentinel 2, the method was slightly different. We had done the NDWI, which is a water index. So that index basically, once we plug in the formula, delineates the water, and then we had used it to basically mask out the ocean from the land and then derive the shoreline. NDVI is basically deals with vegetation. So this time around, the method is slightly different. We'll figure out vegetation area, which would help in determining the edge of the land and subsequently the shoreline. Meanwhile, Tasseled Cap technique utilizes the multispectral band information and transforms it into three types of vegetation specific output, namely brightness, wetness and greenness products. Together, these components aid in the temporal analysis workflows, as is applicable for our shoreline delineation workflow as well. Let me transfer the downloaded Landsat 8 imagery bands into my working folder. And now we are ready to begin the processing phase on ArcGIS Pro GIS software. Let me create a new project. While ArcGIS Pro comes with preloaded geoprocessing tools and toolboxes, the NDVI+Tasseled Cap toolbox is an external toolbox and we'll have to load it separately. We can do so by clicking on Insert at the top of the screen and going to Add Toolbox section and navigating it to the location of the saved tool. Upon selecting it, it is loaded in the geoprocessing pane under our current project. As you can see, there are 7 types of tools within this particular toolbox. Now, one can load the downloaded Landsat 8 images by using the Add Data button underneath the Map tab, or simply just drag and drop it from the folder onto the content pane of ArcGIS Pro, as we will do in our case. All the products have been loaded and these are black and white renditions, and the pixel range is also mentioned underneath each of the layer. We need not worry about the interpretation of these bands, and it is not necessary for our workflow currently. That being said, if you recollect, on Snap I had showed you the true color representation. Remember, this is an optical imagery, so we can do so in ArcGIS Pro as well. We'll have to navigate to the imagery tab, click on raster functions, data management, then thereafter, and finally on composite bands. In the composite bands, we'll basically, it's kind of a, we'll use the which 3 bands are needed for generating the true color imagery. So we need the B4, B3 and B2 band to basically generate a true color rendition of the area of interest in the Landsat 8 cross section. Doesn't this look beautiful? For a moment I thought this was not a true color image and it was just a piece of art, and that is often the beauty with satellite imagery. Actually, this is a natural color photograph. Where is Anjuna beach in this? We can go to the locate tool and use it to basically ascertain. This is where Anjuna beach is located, and those who have seen my previous workflows would associate the memory of this particular location. We'll create a new bookmark which basically would help us navigate back to this location should we basically zoom in, zoom out or go to another view. And this is particularly useful. So let me just zoom out right now. And if we go to the bookmark section and just go click on that particular bookmark we saved, it automatically zooms into the precise location. Anyways, now that we have done viewing the optical photograph and zooming it onto our area of interest, we can begin with the first geoprocessing tool in the new toolbox, which is clip multiple rasters to AOI. Over here, we can club multiple rasters together and then do it, the entire batch processing of it. But for this particular workflow, let me do it individually using a different method. And it has one particular advantage also, which I later on figured out. So instead of using the first tool in the downloaded toolbox, we'll just use the clip raster tool. In the input raster, we'll have to select each of the products, the 6 imagery products, one by one. In the environment, we'll click on any one of the bands because it will select the output coordinate system of the newly generated band, which is in the UTM. It's basically a projected coordinate system. Now this is a utility of the clip raster tool. Basically we can draw our clip raster polygon at this very juncture. This particular polygon basically is used as a subsetting tool. It basically clips the entire, this is the location where we want to basically restrict our processing to. And this particular polygon that has been generated using clip raster tool will also be used for us in our later geoprocessing on this particular workflow itself. Thereafter, we will input that particular polygon on the parameters section and subsequently name the output raster dataset as well. Now that we have done, the output has been generated. And let me close the other previously open products, and you can see that the entire range was basically subsetted to just our area of interest which we had drawn a polygon for. Similarly, we can do the same step for the other 5 imagery bands. And I'll not show each of them right now. It would be a waste of time. So I'll just quickly fast forward it to the spot when I had basically created all the 6 imagery bands clips to raster. Let me minimize the view. We don't need the dataset to be open on our view as well. So let me just close it and locate the clip raster extend polygon right at the downwardmost section of the content pane. Now that we have done with clip raster, we can do NDVI calculation, which is the tool number 4. So we'll have to input just 2 information, what is the red band and what is the near infrared band, which is band 4 and band 5 respectively. We'll name the NDVI file as per our desire and save it in a particular folder of our or database of our choice. Besides that, in the environment section, we can specify. This is not a necessary step, but then I like to be better safe than sorry. So I just click on any of the existing product and ensure that the projected coordinate system of UTM is basically selected. Thereafter, upon clicking run, the NDVI product is generated. Again, we don't need to basically involve ourselves in the interpretation of it, but we can observe that straight away the vegetation is basically highlighted in bright colors and water was basically a dark pixel. So we are quite on our way of delineating the shoreline. The next step is Landsat 8 Tasseled Cap transformation. For this tool to work without errors, we need to go first to the environment tab and update the processing extent. Fortunately, we can do so using our previously generated clip raster polygon. Subsequently, the parameters tab will work without error. As you can see, the red cross has been removed and we can plug in the input rasters against each of the respective band names specified. The clipped rasters, that is. Subsequently, we need to set the location where the newly generated output should be stored, which is the 3 vegetation bands, brightness, greenness and wetness respectively. Again, for the purpose of this shoreline delineation workflow, what these bands are in technical detail need not be understood that much. Essentially, these are vegetation related output and it will help us to delineate land from the sea. The tool is completed running and we can see that the 3 new output have been generated and located in the content pane. Now that we have generated the NDVI band as well as our 3 bands from Tasseled Cap, we are ready to pursue category creation of land and sea. In the input raster band, we will direct it to the 4 new bands, NDVI and the 3 vegetation bands. We also need to specify where ArcGIS Pro should store the ISO class and Dendrog Auto files. These files are by default saved in a temporary location and the tool won't run, but after you save it to a permanent location on your system, the tool will be able to run without error. Now that we have done so, we can rename the location and the name of the output raster, but we'll keep it as default. In the reject fraction, 0.005 is by default, and as per my understanding, we can even make it as 0.0. It wouldn't make much of a difference in terms of our overall output. In the environment tab, we'll just be cautious and update the environment to the projected coordinate system by selecting one of any of our band which is in that system. So the output has now been generated. It's a multicolored output, but soon it will begin to make sense to you. Let me update the base map from the current topography to the satellite imagery base map. Now I will play around with the transparency of this layer. Can you spot what is the output and what does it mean? Essentially, the various colors are overlaying on the ocean and the land features, and you can see that there are distinct colors allocated to them. You can clearly see that colors for value number 2 and value number 3 are located for water bodies, and for the remaining colors they are all located on the land. Now this output is not similar across any of the satellite imagery processing you do, just it is particular for our current Anjuna beach related output. So what we are doing right now is we are recoloring by using the symbology pane. So value number 2 and 3 will color it as blue because it is a water feature, and the remaining ones will color it as green because these are essentially land-based features. Now this is just not an artistic output. This particular revised symbology will be useful in our next tool also. So this particular output, which is comprising of just 2 colors with values 2 and 3 for water and the remaining for land. The classify land and sea will use this revised symbology as well as a particular values which we will specify. So in the input raster, we will use the revised symbology raster. We will name the output as reclassify and save it to our desired location. Now what we need to do over here is for the water pixels, we need to plug in a value of 10, which is the maximum weightage. So this is the value basically. So this is where what we'll insert. So what originally carried a value of 2 and 3 will now carry a value of 10, and for all the land features it will carry a value of 0. So essentially what we are doing is we are masking out the land by using this particular tool. In the no data value, it can carry a value of either 0 or 10. It depends on where the majority of no data pixels are located. So no data pixels typically are for where the cloud cover is present, which basically prevents the reflectances to reach the satellite's receiver. In our case, much of the imagery was devoid of cloud cover, and therefore we can use either a value of 0 or 10. I've chosen to use a 0. Also in the environment, I'll ensure that a projected coordinate system is set as the nature of the output. Let me run the tool and quickly show you the newly generated output. While the color combination has changed slightly, the essential point of distinction is the values of the pixels have now changed. So the green colored area has a pixel value of 10, while land is colored red and it has a pixel value of 0. This conceptually draws us closer to the final step, which is the creation of the shoreline boundary using the tool number 7. We need to use the newly generated reclassified as our input raster, as well as clip it to the mask area of our interest. And fortunately, we had already generated a polygon in our first step, which we can use. Although if that is not present, you can also create a new feature class and draw a shape of polygon over the area of interest and use it as the mask in this particular tool. Subsequently, we can specify where the output shoreline will be saved. And in the number of neighbors to use, which is the algorithm, we can use either 8 or 4. Now here is the reason why I had used the word automatic or manual in the workflow image which I had shown you in the previous step. The reason being is that this tool doesn't work. At least it has not worked in my particular software, and I think it is restricted in some way for this particular software version. It is built for the older software version. Besides that, I can't think of any reason why the tool shouldn't generate a particular shoreline. So which is why I have resorted to a manual creation shoreline, because in this particular tool, the output shoreline doesn't contain any attributes, as in there is no shoreline being generated despite all the parameters being correct. And I had spent literally hours on trying to find out whether I am making a mistake or not. So that being said, this particular shoreline is not very complicated, as in there is not much curvature or not many, water bodies or flooded areas and so on. So which makes the task of manually creating a shoreline all that much easier. And we've used this step before in our previous workflows as well. So all we need to do is basically use the raster to polygon tool to first create the individual pixels into a vector shape. Subsequently, we'll use the polygon to line tool to basically break down the vector shape into vector lines. Raster to polygon conversion tool has successfully run, and the output is displayed on the map view as well as in the content pane. This is an intermediary step. We have just created a vector shapes. Upon clicking, you can see that the entire shape has been selected instead of displaying a pixel value. And information such as length and area of shape is present. There are 2 shapes in our layer. And you can see the outline of the shoreline as well, which we will basically extract using the polygon to line tool, which will break down the shape into individual line segments. We need to specify the parameter. Input feature is the polygon layer. We'll specify the projected coordinate system in the environment. And the new output has been generated. Subsequently, what we'll do is, you can see that there are a number of line segments. We just need to keep those of the shoreline. So upon opening the attribute table and sorting the shape length column in a descending order, we'll go one by one and select the biggest shorelines and see whether it corresponds to select the biggest segments and see whether it corresponds to the shoreline of our interest. It's not necessary that the shoreline is captured in one single line segment. It can be multiple. Fortunately for our case, it is captured in one line segment itself, and therefore we'll delete all the other segments. Our shoreline line segment has been isolated and extracted now. In fact, it extends beyond our immediate area of interest as well. And if you are too finicky about it, you can even use the split tool, which I have demonstrated in my previous workflow as well. You just need to create 2 intersecting line segments where you basically want to cut off the existing line segment, and this would leave you with only the desired piece of shoreline. Anyways, now we can closely monitor the output, and you can see that it reasonably coincides with the satellite imagery base map on ESRI, and as you know, our timeline is 2024 and we are currently in 2024. So the satellite imagery base map is relatively recent as well. That being said, one can also use a better tool to visualize our output, which is Google Earth, because it gives us certain advantages in terms of playing around with the timeline of the underneath base map of satellite imagery. In order to migrate this particular shoreline to Google Earth, we need to first convert it into a KML or a KMZ format. The layer to KML geoprocessing tool, which comes preloaded on ArcGIS Pro, would help us to do this. We just need to put in the input layer of our existing shoreline and save the output layer in a .kml format at our desired location. Besides that, we don't need to enter any other inputs, and we can run the tool, and it is very quick to run. Subsequently, let me show you the output on Google Earth. Remember that we had chosen to use Anjuna beach as our area of interest because we had already done Sentinel-2 analysis and we just wanted to use it for comparison purposes. Now, as you can see, the Google Earth Pro has loaded and it has a provision to select the timeline of satellite imagery by using the historical imagery button. So, on the timeline as well as on the bottom of your screen, you will see the date of the imagery. So, we have captured our shoreline from the January imagery. So as close as we can get to that, that would basically highlight to us whether our generated shoreline basically matches the surface features as seen from a optical imagery of satellite base map. I have also preloaded alongside Landsat 8 shoreline the output of Sentinel-2 shoreline from January 2024 as well. Given that the shorelines were captured from imagery just a few days apart in Jan 2024, as well as Google Earth's base map view is now in the early portion of 2024, the entire setting is ripe for comparison. As I navigate the shoreline, notice the green shoreline, which is from Sentinel-2, and the pink colored shoreline, which is from Landsat 8. Notice the similarity, differences, the potential reasons why, contemplate about it, and which method would you prefer. Personally, I see wherever there is a bias, more or less the shorelines are reasonably close to each other, but wherever there is a major bias, there is a clear reason behind it. Sentinel-2 imagery was analyzed using a water index, NDWI. Therefore, water features are very easily demarcated, and therefore the western edge of semi-water, semi-land features is where the shoreline of Sentinel-2 is. Whereas NDVI based Landsat 8 analysis shows a clear preference for purely land features, and therefore the shoreline is on the eastern edge of semi-land, semi-water features. In my view, Sentinel-2 or Landsat 8 is not the bigger question. The bigger question is which method you are using, and I think NDWI is the better method because ultimately we want to spot the place where the land meets the sea, and NDWI is better placed to give you that particular answer in a right way. Nonetheless, the difference is not very large and one can use either of those methods on either of the two types of imagery. That being said, I also want to bring to your attention that while we had done the last step of NDVI based Landsat 8 imagery analysis using a manual method because the automated tool wasn't working, because our shoreline of Goa was reasonably smooth and without any other terrain, deviations and properties, everything went smooth. But I had done a similar analysis on an area of interest on the east coast of India at a place in Odisha, which was affected by erosion. And you can see that the polygon to line output generates way too many attributes, which is 3754 distinct rows of line segments. Now that is very tedious to manage. I had thought of analyzing this particular region because Odisha as a state is also incredibly ravaged by cyclones and other natural disasters, and therefore its shoreline is particularly prone to suffer from massive deviations and most generally erosion. So this was the news article which prompted me, and I pursued it. And after, because I wasn't able to generate an automatic shoreline, I had created it using the manual method, but I was simply unable to create a shoreline from it because the polygons which were generated were too variable, too haphazard, of different shapes and sizes, and the polylines which were generated subsequently were even too tedious to manage, and it is virtually impossible for me to sift through all these features to identify the common shoreline line segments and to delineate it from the non-shoreline ones. So hence, this is just to inform you that the toolbox is not suited for analysis unless you have a particular version of ArcGIS Pro. Manually only works where the shoreline is of a reasonably smooth texture. With this, we come to the end. Thank you. You'd recollect that towards the end of the previous video, while using the vegetation index-based tasseled cap technique on a particular area of interest, the Satabhaya village in East India, I had encountered a difficulty in extracting the shoreline. The topography was complex. There were several water-related features on land near the coast, such as streams and rivers, which made it difficult to get the shoreline in a single piece. There were numerous line segments, and to isolate and join them manually would have been cumbersome. With the water index based and automated shoreline analysis and extraction tool developed within the European Coastal Flood Awareness System project by the Copernicus program, we will not encounter a similar issue. And in this workflow, I will demonstrate it. The SAET algorithm is adapted from the ShoreX technique of extracting the shoreline from optical imagery, and it has a sub-pixel level of accuracy. Yes, while the Landsat and Sentinel bands are no less than 10 meters per pixel, the root mean squared error of using SAET algorithm has been shown to be not more than 3 meters. Besides the efficiency, the process of shoreline extraction is also completely automated, facilitating ease of use besides other advantages. You can refer this paper on mdpi.com to read more about the process. ECFAS's shoreline analysis and extraction tool is open source. Only recently was it made accessible to the public on July the 3rd of 2023, and it can be downloaded from zenodor.org. As of today, version 4 of the tool is the latest version, and it comes wrapped in a 150 MB zip file, which I have already downloaded. So let me show you the contents of the zip file and an overview of how to install it and things to take into consideration while doing so. Within the zip file, there are a couple of folders, the report folder and the version 4.0 tool. In the report folder, there is a PDF which we'll refer to, and in the version 4.0, there are several files and folders within. Preferably, you must extract the content straight away directly in the C drive in order to avoid complications. Within the version 4.0, there is a doc folder which contains a couple of PDF on the installation steps as well as a README document, and we will refer all the 3 PDFs together in a moment. So first, let's visit the installation document. All the instructions are very lucidly mentioned, and if you follow it, you will not encounter an issue. So Python 3.9.7, that particular version needs to be installed for this particular tool. Thereafter, you will have to create a virtual environment BAT file as well as download the SAET libraries using the pip command line mentioned. Also, in the file sp_config.py, you will have to input your login credentials to download the Landsat and Sentinel satellite imagery, which forms the input in this particular tool, and the procedure is relatively straightforward. On USGS, which is the repository for Landsat imagery, you'll have to place a request to access machine-to-machine interface API. It takes usually 1 day to get this particular approval for Landsat imagery, and for Sentinel, you'll have to go to dataspace.copernicus.eu and just create a login on that particular website for you to be able to access it from the command line interface of SAET tool. So this is the sp_config.py is a Python file, but it can be opened in a notepad, and there is a provision to input the username as well as the password as indicated in the installation PDF file. In case you encounter difficulty in downloading the SAET Python libraries manually in the previous step, you can automate the process here by running the appropriate GDAL Python wheel based on your operating system. Also, here in the home folder, there is an example of use_sp text file, which contains the Python script formats for the search, downloading and processing of Landsat and Sentinel optical imagery. This is a very useful file for future reference as well. If the installation was done correctly, you will now be able to run the virtual environment to download the Sentinel and Landsat imagery. SAET_env_activation is the BAT file that you had created earlier, and the environment has now been created. In this particular workflow, we will use only Landsat imagery, and I will demonstrate it to you. I have not used the Sentinel imagery because it is only downloadable for the European coast, and our area of interest is on the east coast of India in the Satabhaya village, and therefore Landsat imagery is only what we will use. Let me show you the other PDF file which comes with the tool. It is the proof of concept for the ECFAS SAET tool. Very detailed document, and the table of contents is visible. It's about the project, about method of defining a satellite derived coastline, optical as well as radar imagery, the previous methodologies, what are its advantages, disadvantages, and how basically SAET tool helps to navigate the disadvantages and generate a better outcome. So, and it contains the previous research work, the output on Mediterranean coast, the root mean squared error information, as well as the parameters to run, what all the acronyms mean, so on and so forth. So it's a very detailed document, 166 page document, and is useful for running the particular tool. In the output_data folder, there is a folder where all the downloaded data is accessible, both the raw data for the Landsat 8 and Landsat 9 satellites as well as Sentinel-2 satellite, as well as whatever processing we do, the shorelines are also saved in the SDS folder within the data folder. Besides, there is a website on YouTube, or link on YouTube, ECFAS module, SAET Shoreline Analysis and Extraction Tool. It's a 26-minute video, and while it is based on SAET version 1.0, it is still very useful for referral because it's in a video format and very step by step with detailed instructions on not only what is SAET, what is, how basically has it been developed under ECFAS, how to install it, what are the prerequisites, what are the basically the modifications that you have to do, how to run the tool, and as well as how to basically post-process as well as analyze the particular imagery, which is useful. So far in our previous workflows, we have not analyzed the output in terms of what extent the erosion or accretion is there, but we can do that impact analysis using the post-processing steps after running the SAET tool. And those instructions are also mentioned here, and I'll demonstrate it as well. Right. Before we run the Python script to search for and download and process the Landsat imagery around the Satabhaya village on the east coast of India, by running the Python script on the virtual environment, we need to do one additional preparation step. In the aux data folder in our home location, there is a beach polygon shapefile, and we need to edit this shapefile on ArcGIS Pro. The premise is simple. This particular tool, SAET, was developed by European Coastal Flood Awareness System. This particular body basically is in charge of monitoring the European coastline in the case of certain climate-related events such as a storm, flooding events, and therefore the software comes preloaded with the beaches polygon around the European coastline only. What we need to do is add this particular shapefile onto ArcGIS Pro, and we will add the beach polygon around the area of interest which we want to basically download the Landsat imagery for. So this polygon serves only one purpose, which is to basically restrict the software to basically extract the imagery from the online portal for that particular location. So it need not be geographically accurate. It just needs to overlay the area of interest. Let me update the base map on ArcGIS Pro to satellite imagery view from the current topography view. And if I switch off, you can see the outline of the beach underneath the beach polygon. And if I click on the polygon, you can see that it has a beach code attached to it. So there are a total of 8,170 beach polygons which come preloaded with the software package. But none of them are on the Asian or Indian, you can say, coastline. They are mostly on the European coastline, and some of the nations are in and around Africa, where European nations basically have a governing interest. Therefore, let me begin by adding a particular polygon for Satabhaya, and for that I need to first locate it on the map. This is its location. We just need to create a new polygon, so we'll go to the Edit tab and click on Create, and we'll draw a polygon around this particular location of our area of interest. I am not being very particular about the dimensions or the scale. I'm just drawing a polygon around it right now. We need to save the edit in order to save the particular polygon. And if I go to the attribute table now, a new row has been added for this particular polygon, but currently it is empty. Besides the shape dimensions, it is empty. So we need to plug in the buffer distance 300 and the beach code. So this part is the most crucial one. You need to add a unique beach code, which is currently not mentioned. So 8193 is the next in the sequence. So I'm adding that as a beach code. So this is the fundamental step that we need to do. And now we are in a position to run the particular script on the virtual engine. So the name of this particular Landsat imagery, where I had faced problem earlier in the NDVI+Tasseled Cap, the imagery dates from the 2024 3rd of January. And there is also a code, which is the identifier mentioned in the name of the particular imagery raw file. So when I go to the examples of use text file, underneath the searching for Landsat imagery, the parameters which I need to enter are central date, which I want to monitor, and two bordering dates, beginning and ending around that, a cloud level percentage, and the type of product which I want to do. And the scene identifier is the six digit number which is used to identify the scene. So this is the only input parameters that we need to work in, and this is the particular code by which we will tweak that code to search for the Landsat imagery of our choice. So let me copy this particular code and paste it in a Word document so that I can show you how to edit it subsequently. (139.046) is the identifier. And because I know which date of imagery I wish to download, I don't need to basically, and just let me show you that on Earth Explorer USGS website. This is the product that I'm referring to. It again has the same identifier. So I'll replace the current default identifier mentioned with the product identifier of our choice. Ensure that there are no gaps between the digit and the function command. Subsequently, I know I have to put the start date, central date, and end date. So typically, when I know the date of imagery that I want, the start date and end date can be 1 day above and below the particular central date. So my central date is, I've inputted that. In terms of cloud cover, I know that the cloud cover is less than 1%, and in optical imagery, as you would know by now, that we don't need cloud cover. It will basically tamper with our workflow. So we need to put as minimum cloud cover possible. Fortunately, we know that our imagery of choice has a cloud cover of less than 1%. So upon entering this particular information script onto the virtual environment, the software begins to search on the USGS portal via our API that we had requested earlier and got approved, and it shows me the search result. This is the exact same product. It is currently showing as product number 0, which is the same as what we want to download. As you can see, the product name is one and the same. So it basically gives us a visual cue by showing us the search result, whether this is the particular imagery we wish to download. So our search results were accurate, so we can now proceed to download the Landsat imagery. So for that also, a particular Python script is mentioned in that text document. We need to run this script and also specify what is the number of the unique identifier number of the image. So let me demonstrate it to you. This is the script. So as I run it, it will ask me which of the search result you want to download. So currently there is only one search result with the name 0. So I just need to input 0 and enter, and the imagery will begin to download. The actual length of download depends on your server bandwidth, etc. But then it's a typical, this file is 945 MB and it will download it in full. And once it is completed, I am fast forwarding it. It will unzip it and place it in our output folder under the data section. And I'll show it to you where it has downloaded. It is exactly the same output. If you would have downloaded it manually from USGS website, the output is stored in the exact same format under the Landsat folder. So I had done some previous working, so those workings are from there. But then there are two satellites, Landsat 8, Landsat 9. So in the Landsat 8, you can see that our product from 3rd of January 2024 has been loaded and all the imagery bands are there. And we now need to process it. And the best part of running this SAET tool is that we don't need to use any software. We just need to run another script, and the software will basically internally process it and just generate the output of our choice. So this is the processing script that we need to enter with a particular parameter, which is what is the segmentation. So if you're aware, we used to do thresholding. We used to select a water index in one of our previous workflows. I'll just show you what it is about. So there are several types of water radiometric indices. We had experimented with the MNDWI before. NDWI is natural difference water index. This is modified normalized water index, MNDWI, and the advantages, disadvantages are mentioned. And AWEI, which is automated water extraction index, is what we are going to use because it has certain advantages which could be beneficial for us, as it removes the shadow pixels and so on. So this SAET tool runs predominantly on SWIR, which is shortwave infrared band. The algorithm is based on that, and I believe that we can use the AWEI NSH as our processing method basically. The parameters which we need to enter besides that segmentation method is our area of interest beach code, which is optional, but it is preferable to do so because it will reduce the time of processing. So let me paste that code. We just need to change MNDWI, which is the default parameter. It's not a default parameter, it's mentioned in the script currently. I'll just change it to AWEI NSH. And in the beach code, if you remember, in our polygon, the new polygon which we had created, the beach code which we had inserted was 8193. So that is the reason why we need to remember it, and we'll plug it in once again onto the script so that the portal will only search for images which are underneath, which has an intersection, you can say, with this particular beach polygon. Subsequently, it will ask us and which image to process, and we'll have to enter the number. Let me paste the script in the Python virtual environment and run it. There are currently 4 output, 3 from Landsat and 1 from Sentinel in my data folder. 3 of them are from my previous working, so I'll have to be specific which particular file which I want to process. So it is the dataset number 1, which is from 3rd of January 2024. which I want to process, and I'll enter number 1 in the parameter, and it will begin processing it. The processing steps take some while to perform. I am just fast forwarding it, but you can see the steps involved: water index band, cloud max computation, water index mass, rough pixel line, read projection, clipping, rasterizing, extracting points, averaging it out, and so on. So finally, once the processing is done, the shoreline shapefile is saved in the SDS folder. SDS stands for Satellite Derived Shoreline, and the folder is preloaded only on the tools folders. Under output data, there is a SDS folder, and the output has been generated and stored in this particular folder. So now we can, now that we have processed, and what we should have as an output is a shoreline, which is underneath the polygon of our choice on Satabhaya village on the east coast of India. Let me open ArcGIS Pro once again and load the shapefile. There are two shapefiles, the line shapefile and the point shapefile. Both of them would be of use to us. Let me just load the line shapefile first. As you can see, there is a clear, distinct shoreline which has been generated. Isn't this marvelous? The output from my previous workflow, there were dozens and dozens of line segments, but this one looks like a single shoreline. Not that it is completely accurate. You can see that some of the shoreline portion is extending onto the land area as well. We can modify it if we want to at a later stage, but the most important point is, once I open the attribute table, is it's one single shoreline. So I don't even need to join two different line segments together. It is one single shape. So this is one major advantage of using this particular tool. Now, I also wish to show you the shoreline on the prevalent, or you can say the satellite imagery during that particular time frame. So I'm just exporting this particular layer file because the base map satellite imagery, I don't know from where exactly it is. I can find it out, but then it's unlikely to be from 2024 January. So I wish to see the shoreline on the correct, you can say, proportionate satellite imagery. So I'll just export the layer file to KML. This KML file, I can load it onto Google Earth. I've named it as test, and on Google Earth, the benefit is there is a possibility that you may get to overlay the output on a base map from that particular timeline, and we'll try to do so. You can see that our KML file has been loaded and the shoreline is on the Google Earth base map. The imagery date, it's a stitch. This Google Earth base map is done via stitching multiple imageries. So the imagery date in our, you can say, area of extent is located on the bottom part of the screen. You can see the current imagery date is from the 4th of September, 4th of August of 2023. So I'll just play around with the imagery timeline to see if there is any imagery from January of 2024 on this extent. Around Satabhaya, I don't see anything, but then I can just navigate around the shoreline to see if I can spot the correct imagery base map from that particular timeline. Let me hover a little bit towards the south. You can see the imagery date right now is from February 2024. And this is much closer to January 2024. So let's examine the coastline closely. Is it accurate? I had indicated to you that the pixel value is typically within, there is a root mean square error of 3 meters per pixel. So currently, if my assessment is the shoreline is reasonably accurate around the coast. Remember that this is a water index, and in the water index there is a slight bias that semi-water, semi-land features. The shoreline will be on the seaward edge of the particular feature. So more or less, in my opinion, the shoreline is reasonably accurate. Intuitively, it is logical to validate the shoreline which was extracted from optical imagery using the optical imagery raw dataset itself rather than scouring for appropriately timed base map on Google Earth or other platforms. So let me try it out. I've imported the B4, B3 and B2 bands from the Raw Landsat 8 imagery from where this shoreline was extracted. These three bands can be composited together here on ArcGIS Pro to generate a true color, that is a natural photograph view of the terrain. So let me click on imagery, raster functions, and under the data management section, let me click on the composite bands geoprocessing tool. So within this, the input rasters will be the three bands B4, B3 and B2 respectively. And these three layers can be combined together as a composite to generate a new layer which would look like a natural photograph, as you can see on the screen over here. And we can use this to basically visually inspect whether the generated shoreline is accurate or not. So as I navigate across the screen, you can see that where the blue pixels end, that is where the shoreline has been generated. So broadly speaking, it is appearing reasonably accurate. One doubt which one can have is what are those white pixels and whether that should be constituted as land or sea and or not. So this is something which we can validate it. So how we will do that? We'll just switch to Esri's default satellite imagery base map, although it is from a different timeline, but we can see in a much more clearer manner because this imagery is of a much higher resolution. So we can understand the properties of the area and then try to discern from our generated composite layer whether the shoreline is accurate. So over here you can see that there is this stretch of the land, there is a white pixel, and as I toggle the views, it is very evident that there is a beach over here. So naturally the beach will not be formed as a part of the coastline, so the edge of the beach will be held as the coastline. So the rendition appears accurate. So let me just go to another section of the shoreline. Over here there is a high density of water pixels, and let me toggle the views. So over here again you can see that the beach feature is extent of the beach feature is where the coastline is drawn, and waves and other aspects which are, you can say, light white pixels, those are on the sea. So those are correctly not utilized for the shoreline. Therefore what we can conclude is that the NDWI index derived shoreline from Landsat is reasonably accurate. Now in parallel I've also downloaded an imagery from 25th of December 2020, so which is around, you can say, 3 years ago. I'm not showing those processing steps. I've just generated using the same steps the shoreline, and I'm just loading it side by side. So now we have two shorelines where we can basically compare. Now previously we used to do visual comparison. This time we'll take it one step forward and do some actual quantitative analysis, which is gonna be fun. So the red colored shapefile is the shoreline is from 2020 and the yellow one is from 2024, and you can see that there is erosion around the coast, which was also indicated by the news article which we were referring to. The Satabhaya coast has been ravaged by coastal erosion, which is basically hampering that fishing village. I can do a rough and measurement. So you can see that at this particular zone there is a 55 meter gap between both the shorelines. But then in order to do something which is scientifically can be held as a valid output, we need to do something better than this. So let's proceed to do that. Now this particular processing step, I will do it on QGIS, not on ArcGIS Pro. So in order to do that, we need to first, I would prefer to clip the shoreline. So I don't want to do the analysis on the entire shoreline. What I'm doing is searching for Satabhaya and will clip the shoreline to a particular, you can say, extent around it only. Let me measure the shoreline extent in this particular view, that is. So half the image view is around 1000 meters. So roughly speaking, if I were to extend it, it would be around 2000 meters of shoreline would be something which I will demonstrate it to you, how to do some quantitative analysis of the extent of erosion, or if there is accretion, we can measure it as well. So in the output file, there was a line file and there was a point file as well. So the point shape file, we'll just load it onto ArcGIS Pro. The analysis has to be done using this particular point data. So the point is the actual output from the tool, and the line is basically, you can say, a segment which basically links all the points together. There are thousands of points right now in that particular shapefile, and we'll now clip it. And in order to clip it, what we will need to do is to create a polygon for clipping it. Prior to that, let me add the point file from 2024 as well. So now the point shapefiles of the shoreline from both the timelines have been added onto ArcGIS Pro. Once again, we'll just clip around 1500 to 2000 meters of the shoreline, and I'll demonstrate the analysis portion to you on QGIS. I'm going to databases beach_polygon and creating a new feature class, which will be my beach extend polygon, which I will clip the point data set. I'll just uncheck Z values, which is the height values, and just go to the final step, finish it. The raw dataset, empty dataset has been generated, and I'll create a polygon now by clicking on the create button underneath the edit tab. So around the shoreline of our choice, I have just created a rectangle, and now I'll use the clip tool to basically clip the point data set. I have not saved this new file, so it's very important that whenever you create a new polygon or edit a file, you hit the save button, and not on the main save button, but underneath the edit tab. So I'm just doing that. In the input feature or dataset, I am first clipping the dataset from 2020. I'm using the beach extend polygon as a clipping feature, and I'll name the output dataset as per my choice. December 2020 _ clip. The output has been generated, and let me repeat this same clip geoprocessing tool on the 2024 dataset. Right, both the clipped point shapefiles are there, and I'll just close all the other layers so you can see the clip has worked out successfully. Now there are only 260 points. Earlier there were in thousands. Now only 260 points are there in one layer from 2024, and 243 points are there from the other layer. So how do we go about doing the quantitative analysis? First, let me export these clipped files as shape files so that I can load it onto QGIS. However, before that, I need to do one additional step. As part of the quantitative analysis, we need some reference line to basically measure the extent of change. So I have just created a new empty line shapefile, that feature class I have added. Even before drawing that particular line around the shoreline, I'm just modifying its symbology so it appears prominent. Now I'll go under the edit tab. I'll create this particular feature. So the name of the line feature is reference line of the inner beach. So I am basically drawing a line on the inner side of the beach, very close to the shoreline, but whose boundaries extend beyond the shoreline, both at the beginning and at the end. So I have created that line feature, and as you can see, it extends beyond the shoreline. The idea is to divide the reference line into equally spaced line segments and subsequently measure the distance between the shoreline points from both the timelines to the nearest sector on the reference line. After this step, we can average out the net of the distances to find the mean accretion or erosion level for that particular sector on the reference line. So the first step which we need to do is go in the Edit tab and click on the Divide tool. I had used the Split tool earlier, that was incorrect. We have to use the Divide tool. As you can see that there are 3 ways which we can divide based on distance, parts or percentage. We'll divide it into 10 equal parts. So the line which is reference line, which is around 6,500 feet or 2 kilometers or 2000 meters, I am dividing it into 10 equal parts. So now the entire line is divided into 10 different line segments, as you will see from the attribute table, and each line segment has a length of around 183 meters. So now we have created those segments, and we also have our clipped shoreline points, and we can now export this as shape files to be loaded onto QGIS. But prior to that, just one last step. We'll create one new column called DLFID_INT in the reference line shapefile. What the reason we are doing it is for a subsequent processing step, and after we have created that particular column, we'll just name it as it's basically a unique identifier for each of the individual sectors. So we'll name it as 101 to 110, basically 1 to 10, but above 100 is the identifier. So this will be the unique, you can say, code given to each and every sector, and we can use it subsequently to identify what is the mean erosion or accretion for each of this uniquely coded sectors. Done. We have done so, and we'll save the edits. We'll right click data, export features, type in the name and location of our shapefile. I have already created a test folder on my desktop, so I will save the contents over there. It is important to suffix the name with a .shp, which is a shapefile format, for the export features to save it as a SRE shapefile format. So I have exported the reference line, which I had divided into 10 equal parts, as a shapefile. Now I will do the same. I'll export the shapefile for the January 2024 shoreline points. And finally, I will do the same step for the December 2020 shoreline points. All our 3 input layers have been exported as shapefiles. So now we can open QGIS and load these particular shapefiles and process it further for quantitative analysis. Let me close ArcGIS Pro and open QGIS. I am using QGIS 3.4 version, but you can, I think, use any of the versions, older or newer, to perform the same quantitative analysis. Once QGIS has opened, I will load the 3 files, shape files. I'll sort the folder by type and the 3 shape files. I'll just click all of them together and paste it in the layers pane. And I'll also, underneath XYZ tiles, I'll add the OpenStreet base map. One can also have a satellite imagery base map over here, but I'm not being too picky. Moreover, I'll do the final, you can say, symbology and artistic endeavors on ArcGIS Pro because I'm much more comfortable using that particular software, as it gives us more, you can say, functions, features, and there's an attractive quotient about it. The first quantitative analysis step that we'll do is to use the distance to nearest hub points tool. So in the source points layer, I'll select the shoreline points from 2024. In the hubs layer, where all my sectors are there, that's the ref line layer, I'll click on it. And in the hub layer name attribute, which I'll basically use the DLFID_INT, that particular column which I had inserted in the last step of ArcGIS Pro. I'll save the file as DTH 2024 and I'll run it. The output has run successfully, and I'll just repeat the same step for the December 2020 shoreline points, and subsequently I'll show you the output as well. So this particular tool helps us to find the distance between the shoreline points to the nearest segment on the reference line. In the output attribute table, focus on the newly generated hub dist column, which contains the distance between the shoreline point to the nearest sector on the reference line. Total 260 shoreline points were there in this layer, and hub dist has been computed for all of them. And in the other output, total 243 points are there, and hub dist has been computed for all of them as well. So now we can proceed to the next step, but let me just make one edit because the newly generated layer output has not been named correctly due to some technical glitch in my QGIS software. I think I'll just remove the 2 layers and reload them so that I can easily visualize the output as per the year. So 224 and 2020, both the layers have been added once again with the correct names onto the QGIS layer panel. The next step is to summarize the results, which is the hub dist, based on the sector name. And in order to do so, there is a particular tool which we will use. It is called statistics by categories. So over here, what we'll do is use the 2024 distance to nearest hub output layer. We'll calculate the statistics based on the hub dist, which is the distance, and the category is the hub name, which is the name of the sector. So we are just summarizing the results to each sector on the reference line, that is. I'll save the file as category statistics 24, short of it, catstat24, and we'll run this particular tool. Before showing the output, let me repeat this same step for the 2020 layer. Once again, I will summarize the hub dist, and the category which I will summarize it to is the hub name, which is already there in the parameters. I'll just rename the output and save it to the desired location and run the tool. Both the output has been generated. Once again, both the layers have basically the same name. I'll just remove it and just add it back once again so that I can distinguish between the 20 and 24. The correct layer names, file names have now been mentioned. Let me show you the output. So in the output against each of the 10 hubs, the total number of count of points which are attached to it, as well as the mean distance of the total number of points is distance to that particular sector is also mentioned. So we are just only interested in the mean at the moment, and you can say partially the count, but mean is the most important column. The rest is not of that much importance to us. For the other CATSTAT 20 also, the result has been generated in the same format. Now finally, we will use the join attributes by field value tool. We'll use this tool twice. So firstly, we'll use both the layers now. We'll join both the layers. So we'll use CATSTAT 20, the older layer, as the input layer, and the input layer 2 as CATSTAT 24. The field name, which we'll summarize it, is by hub name. And what we are essentially doing is doing a, you can say, comparison between the output of both the shoreline points. So we'll use a prefix called post underscore, which will help us to distinguish 2020 from 2024. I'll just save the file of the output and hit the run, and I'll just show you the result, which will be easier for you to interpret what we are essentially doing by using the join attributes by field value processing tool. Let me open the attribute table. Now what has happened right now is both the layers have been joined together as per the hub name, which is the common denominator. The columns with the post as a prefix belong to 2024, whereas those without it belong to 2020. So we are interested in basically taking a difference of the mean distance from 2024 to 2020. So as a result, we'll just hide all the remaining columns and let only the post underscore mean and just the mean column, which is from 2024 and 2020 respectively, be at the front of our eye. Thereafter, using the field calculate tool, we'll create a new column. We'll name it as difference, and the formula is subtract post underscore mean from the mean. So we just need to type that out, and QGIS will automatically calculate the values for the entire 10 rows, which are basically for all the 10 hub names. What is the average difference of the mean? You can see the output preview minus 3.69. So which indicates for the first row, the difference is minus 3.569 equals to erosion, that is. So a figure in minus in 2024 minus 2020 indicates erosion, and all the 10 rows has a negative value. So you can see for each of the 10 sectors there is erosion. Not a single sector is unaffected, nor has any sector along that 2-kilometer coastline that we had shortlisted has accretion between 2024 January and 2020 December. Now I'm just creating a new field in this same attribute table. Because the field has been named hub name by the formula, I have to rename that hub name to DLFID underscore INT. So all I have done is made that new column and linked it to hub name. Now that the hub name DLFID INT has been integrated, I'll just use the join attribute by field value again tool. All what I am doing is linking the reference line layer to the previous layer output, with DLFID underscore INT being the common denominator. Remember that the reference line layer we had inserted the DLF unique identifier in the ArcGIS last processing step. So because hub name was not part of that attribute table, so we use this particular tool to essentially join both the layers using this, which will aid us while we are doing the symbology. So if I go to the layer property of the newly generated output, and instead of single symbol, I use it a categorized symbology. I categorize it by DLFID underscore difference column, which is the erosion levels. And I'll put a color pane, a color ramp, let's say light red to dark red. And then classify. So by default, 10 classifications have been generated. And you can see for each of the sector, what is the erosion level. The darker that reference line, which means greater that erosion for that particular section of the shoreline. Now I prefer, as I had indicated to you earlier, to use ArcGIS Pro for the symbology because it gives me a wide variety of options and it is also user friendly. So in order to do so and in order to make the output much more presentable, I am just exporting this joint layer onto ArcGIS Pro. So I'll export it as a SRE shapefile. Let me load it on ArcGIS Pro. I hope you understood the importance of using QGIS and how quantitative analysis helps to generate more meaningful results. Previously, we had done visual analysis, basic level of measurements, and so on. But this time we are doing a proper, you can say, quantitative analysis. And frankly, if we had made more sectors, we had just used 10 sectors, which are with a large size, 180 meters each. If we had split the reference line into much more sectors, then our analysis would have been much more quantitatively better. The output would have been even more specific, that is. So what we can do after loading the newly generated reference line, we'll just symbolize it as per the category. So I'll use the graduated colors. In ArcGIS, you get a ton of color options. You get to decide the method of classification, the number of classes, and all of it in a user-friendly manner. I'm sure QGIS also has the same features, but ArcGIS Pro is much more, in my opinion, much more user-friendly. So I prefer to use it. So you can basically classify it as per equal interval or quantiles or standard deviation and so on. Personally, I even create my final output maps using this particular software. So it becomes all the more important for me to do the final stage of processing, post-processing on ArcGIS Pro. So I'll not take you through these steps. I'll do it behind the scenes, but I'll just show you the output final map, which could be very useful for as a presentation material as well. So this is the layout, and I'll just make few modifications. This is the final output. You can see the mean erosion across the coastline, be it from 1 to 10 meters, and the stretches, the sectors on the reference line has been color coded accordingly, and the location on the map, the inset, the scale, and everything, the name of the output, where it has been sourced from, everything is mentioned in the final output. I hope you enjoyed the impact analysis stage of the demonstration just as much as the autonomous extraction of the shoreline using the SAET tool. Thank you. In the previous workflow, I had used the SAET tool to automatically extract the shoreline around Satabhaya in Odisha across 2 time periods 4 years apart. Subsequently, I had quantitatively measured the rate of change as well. I had done so by creating a 2 km long reference line parallel to the coast, splitting it into 10 segments of 200 meters each, and then measuring the average distance from the extracted shoreline points to the nearest segment on the reference line. The final output is displayed on the map here. In this video workflow, which is the 7th in the series, I will perform a more refined change analysis and even attempt predictive analytics using a recently developed tool called Endpoint Rate for QGIS. But before that, let me quickly highlight the narrative and evolution of the techniques that I've covered in my previous 6 workflow demos on shoreline detection and analysis using remote sensing thus far. In the first workflow, I demonstrated a basic visual method using the historical imagery tool available on Google Earth software to spot the development of the shoreline over a period of time. While rudimentary in nature, this technique has a particular benefit. It allows a user to quickly gain a perspective of the area of interest, which is useful prior to deep diving with more advanced tools. In the second video workflow here, I had demonstrated a technique to do a better form of basic visual detection and trend spotting using a satellite imagery web interface called Earth Observation or EO browser. This platform allowed me to view the optical satellite imagery for the desired timeline over Marina beach in Chennai, Tamil Nadu, and even visually delineate water from land using a water radiometric index known as Normalized Difference Water Index or NDWI. Subsequently, I was also able to generate a time-lapse video of the imagery across multiple timelines. In the third video workflow, I had gone one step further. I had actually downloaded the Sentinel-2 optical satellite imagery over the area of interest in Anjuna Beach, Goa using the Copernicus browser. Processed it using modified and better water radiometric indices on the open source Snap tool here. And finally, also what I was able to do is to actually extract the shoreline over the 2 time periods using the premium but the trial version of ArcGIS Pro GIS software. In the fourth workflow here, I had downloaded for the area of interest, which is Vizag coast in Andhra Pradesh, a different type of satellite imagery from the Copernicus browser. This type of imagery is known as SAR or simply radar imagery, which has a unique feature in that it is able to collect the Earth observation information even at night and remains unaffected by weather conditions such as cloud cover. Subsequently, I had delineated land from sea by applying a set of geoprocessing commands and a digital elevation model or DEM based algorithm and refined it further by thresholding the reflectances. Even here, the shorelines were extracted using ArcGIS Pro. While all the previous 4 workflows were performed using satellite imagery from the European Space Agency's Sentinel platform, in the 5th workflow here, I have used a different source of optical satellite imagery, that is Landsat satellite imagery from NASA USGS platform. The area of interest remains the same, which is Anjuna Beach in Goa, which I had used in the previous workflow. I had processed the Landsat imagery and on ArcGIS Pro using the Tasseled Cap technique, which involves the use of a vegetation index instead of a water index. The vegetation index is called NDVI, and I had used the vegetation index to delineate land from water. Finally, I had even compared both the output of the derived shorelines from Sentinel and Landsat imagery on Google Earth and shared my observations on which is better, what are the advantages and disadvantages. And finally, as I had indicated at the very beginning of this section of the video, in the 6th workflow, I had demonstrated a very handy tool, the Shoreline Analysis and Extraction Tool, or in short, SAET. It has been developed by European Space Agency under its ECFAS coastal monitoring platform, and it not only allows a user to automate the download process of Landsat and Sentinel optical satellite imagery by running a straightforward Python-based command, but also it allows us to run a custom algorithm to extract the desired shorelines over the area of interest from the raw imagery just as well. Our area of interest was in Satabhaya in Odisha, and the beauty is that the entire workflow from download to processing to extraction can be completed in just about 10 to 15 minutes, and it generates a consolidated, breakage-free and a reasonably accurate shoreline for the area of interest. Post the shoreline extraction, I had even measured the rate of change across the 2 timelines by creating a reference line and performing distance-based quantitative analysis using the open source QGIS tool and refining the visual map-based output subsequently on Esri's ArcGIS Pro platform. The 7th and final workflow that I'll cover shortly is the endpoint rate tool for QGIS or EPR4Q, a recently developed algorithm used in scientific coastal research. There are several other powerful tools which deploy similar or different techniques that I have not covered in this series. Some of the notable ones are, beginning with perhaps the most popular one, the DSAS or Digital Shoreline Analysis System by USGS. Its methodology involves casting transects and then calculating the endpoint rates just as the EPR4Q tool. Unfortunately, DSAS only operates on a historical version of ArcGIS Pro, the ArcMap commercial software that I do not possess. The transects technique by itself is not too difficult to grasp. It basically involves taking 2 or multiple shorelines over different timelines. Subsequently, we have to draw a seaward and or landward baselines or reference lines parallel to the shore, and then we have to cast perpendicular lines onto the shoreline from the baselines. DSAS and EPR4Q tools basically are automated ways to cast transects over large areas at tiny distance intervals, which basically enhance the accuracy of the quantitative results. The rate of change, regression, and other types of statistics are calculated subsequently by measuring the distance between the transect intersection points on the shorelines considered. Besides DSAS, there is also the UMBUR, which is analyzing moving boundaries using R. It basically uses the R analytics package, something which I'm not familiar with, and hence I have not given a demonstration for this. CoastSat is another algorithm which is used in scientific coastal research. It's an open source software written in Python, and it can perform various different types of advanced analytics such as shoreline extraction, accuracy assessment, basin scale mapping, beach slope estimation, and so on. Again, I am not familiar with this tool. There are commercial, you can say, workflows available also, such as the one developed by S3 Industries that is displayed here. It involves using machine learning and deep learning techniques for coastal line extraction, and it comes integrated with their Marine module, basically, which is a paid, you can say, extension of their commercial software ArcGIS Pro. So you can look up and observe the video on YouTube, which is available, which contains the tutorial for this particular workflow as well. So these are some of the tools involved, and there is also one more, which is ShoreX, and endpoint rate tool is basically using ShoreX on an open source software, which is QGIS. EPR4Q was developed by Dr. Lucas Teres de Lima and his fellow researchers at Center for Environmental and Marine Studies in Portugal. This paper presents the efficacy of EPR4Q tool compared to other popular methods for coastline research, such as DSAS and UMBUR. While the former uses a commercial software, the latter is technically complex to operate. Hence, the need for developing this tool was felt. Overall, a high degree of correlation was observed between these methods, and this method is proven to be useful on linear, extensive, and non-extensive shorelines. Let me present to you the definition of endpoint rate. It is basically the mean annual rate of shoreline change in meters per year, and is calculated by dividing the distance of the shoreline movement by the time elapsed between the oldest and the most recent shoreline. A very complex looking methodology is basically the premise of the EPR4Q tool's algorithm. It involves the casting of the transects, calculating the beach angles, and creating buffers, and so on. So you can see the multiple, you can say, processing steps that are involved in analyzing the shoreline from this graph. As I had indicated previously, a high degree of correlation was observed between EPR4Q and the other two popularly used tools for doing shoreline analysis. One thing that I would like to highlight is that all these tools do not perform that well on embayed shorelines, which is basically this type of curved shoreline. It's basically difficult to cast transects and perform measurements on these types of shorelines, and I had wished I had known this fact, because I had racked my brain for hours, if not days, on a particular type of shoreline similar to embayed shoreline, which I will also demonstrate in brief later in this video workflow. That being said, this tool is completely free to use and open source, so that it can be developed by researchers further, and I'll definitely recommend you to use it. Our area of interest is Satabhaya, and we had already done quantitative analysis for that, and we'll continue doing that using EPR4Q. And to do that, first we have to download the latest version. Currently it is version 3.4 of this tool. Can be downloaded from zenado.org. Certain instructions also have been mentioned on how to install and what are the parameters involved. I have already downloaded this tool and extracted its contents. There are basically the model file as well as the symbology or the result, you can say, output design files. On YouTube, there is a tutorial developed by the founder researcher, Dr. Lima, and while it is narrated in Portuguese, you can also use the English subtitles. Nonetheless, one of the reasons behind using this tool is to present a English version of this particular tutorial and quite hands-on in that manner, so that it can be more accessible to enthusiasts and researchers. On ArcGIS Pro, the previous results are displayed over here. The Satabhaya shorelines from 2024 and 2020 are basically displayed, and I have used a beach extent, basically a 2 kilometer long polygon from the entire coastline. We'll restrict our analysis on that 2 kilometer stretch, which I had even used in the previous workflow. Satabhaya is kind of right middle at the bank of this particular extent. Now we already know that Satabhaya is very hardly hit by coastal erosion, and it kind of eases, gives us a perspective while we do our analysis. The measure distance tool indicates that the length of the chosen area of interest is just a shade under 2 kilometers or 2000 meters. While I will not be taking you through the steps that I had used to create this beach polygon, but just to highlight that I had done so by creating a new feature class in the default project database. The feature class was in a polygon shape, and upon creating it, I had manually drawn the beach polygon over the area of interest. And I'll use this particular feature to clip the existing two shorelines. I'll use the clip geoprocessing tool, and in the input feature or dataset, I'll select the shoreline from 2024 first, and under the clip features, I'll use the beach extent polygon. I'll repeat the same step on the shoreline from 2020 as well, and I have both the shorelines now available. Let me update the base map to the satellite imagery view. The red colored shoreline is the recent shoreline, while the blue colored shoreline is from 4 years prior. Now let's begin with the next step, which is to manually draw the reference lines or the baselines. One is on the landward side and the other one is on the seaward side. So let me begin by landward side. I'll create a new feature class, select line as the type of the feature, uncheck the z values because we do not need height attributes, leave the fields as default, and this is a very important step. We'll have to convert the default geographic coordinate system projection to a projected coordinate system, PCS. We'll use the UTM grid, which basically is in meters, and the way to identify can be several, but I'll use the snap tool, and in that I've uploaded as an input my existing satellite imagery, and using the reprojection tool, as I select UTM WGS 6084 automatic option, you can see at the downside of the screen, the CRS is updated to UTM zone 45. So I know that my area of interest lies in UTM zone 45. UTM stands for Universal Transverse Mercator. It's a commonly used projection system which is effective on geographic information systems. So I'll select the UTM zone 45 from the options available. Because it is in the northern hemisphere, the zone is UTM zone 45N. So this is an important step, without which, if you don't do this step for all the layers, the EPR4Q tool will not operate function very well. So be very careful that you have to do this particular step. Subsequently, I will manually draw the landward side baseline. And once again, an important aspect is this particular baseline should be very, very close and run parallel to the shoreline. So it should not be at a large distance. So basically it's the inner edge of the beach, you can say. So and another important aspect is that the end points, the starting as well as the ending points of this particular feature should extend beyond the area of interest shoreline, that is. So it should be very close to the shoreline and it should extend beyond on both the edges. These are the two important considerations which you should keep in mind while creating this particular feature. Subsequently, I'll repeat the same step and create a seaward, you can say, baseline reference line. So both these reference lines will be used as the base to basically cast transects onto both the shorelines from 2024 and 2020 respectively. So I've done this particular step in a fast forward mode. Ensure that you save the edits after creating this feature class. And the length of both the landward and seaward baseline should be similar, and both should be close to each other with the edges extending beyond the length of the shoreline. I will now use a different tool, QGIS, on which the model will run. And as I export it, while the seaward and landward features have been already reprojected onto a Universal Transverse Mercator PCS, I'll just have to export the features as it is. But while exporting the default shorelines that we had extracted from SAET tool, we need to ensure that we update the environment under export features to the 45N Universal Transverse Mercator grid. So all the 4 layers, we only require 4 inputs: the historical shoreline, the current shoreline, and the 2 baselines. And all these 4 layers should basically be on the same output coordinate system. And I've used UTM zone 45N. One another important aspect is, as you can see in the attribute table, there is a beach code, a shape length in the shoreline, as well as in the landward and seaward we had kept it as default, so the shape length is there. Now another important consideration while running the EP4RQ tool is that all the attributes in all the 4 layers should be erased, and there should be just one, you can say, row which contains null data, you can say 0 data, and I'll show you the way to basically do so. Let me open QGIS 3.4.3 with GRASS 7.4.2 software version. Again, the preparation side of using this tool is very, very important, and I had racked my brain for hours, if not days, and even consulted Dr. Lima because I was facing errors in using this tool. So I received the indication that he had developed the tool on this particular format, on this particular, you can say, version of the software, and I am using the same version of the software. One can download this version freely from the QGIS website. And this is very important because the model seems to run the best, or you can say most effectively, without any errors on this particular version of the software. Once I have created a project file under the processing toolbox display of QGIS, I'll first of all load the downloaded model file. So I'll navigate to the folder where I had downloaded the algorithm and click on the model. So the model EPR4Q has been loaded. Just let me show you the graphical representation of the model, which I had also earlier shown you on the research paper. It's mentioned in Portuguese, but you can see that it's a massively, you can say, complex looking software. There are several processing steps involved, and Dr. Lima and his colleague researchers have developed this particular tool. One can, if one has the wherewithal, one can even edit this tool in the way one wants. Now, this is not a mandatory step, but to be on a safer side, what you can do is install a particular QGIS plugin. Visit the plugin pane and search for Processing Saga Next Gen Provider. In case you are using QGIS version 3.4.3 as I have recommended, you will be offered to download Saga 7.2. Now, this is what you should install, and subsequently also search for Saga 7.2 binaries on Google, and you will be redirected to sourceforge.net, from where you can extract the zip file of the binaries. Thereafter, you can extract the content of the zip file in a folder of your choice, and then under the processing toolbox in the options pane, go to providers and click on Saga NG, and in the Saga folder, link the path to the extracted folder. Now, this step is mandatory, which is to go in the general section of the options pane, and under the invalid features filtering, just ensure that the ignore features with invalid geometry option is selected and not anything else. This is an absolutely mandatory, without which the model will not run properly. Now that we have more or less prepared the QGIS, we are now ready to do the processing. What we will do is the 4 inputs, both the shorelines and both the baselines. Let me add it to QGIS. I have a base map of OpenStreetMap. You can use any base map that you like. That's not relevant. Let me symbolize the baselines in a different way so that it can be distinguishable from the shorelines. Now, what we will do next is revise the attribute table. Go to the attribute table. You need to make an edit. We don't need these attributes. Delete all of them, as the model will not, will encounter an error if you run it in this way. Add a field and type ID with a capital I and a small d and click OK. And in the ID, in the first row, type in 0. So essentially, you need to have only one column with the name ID, and within it, the value should be null or 0 basically. And you have to repeat the same steps for all the 4 layers. This is again an important step. Let me fast forward it. I have already done these following steps, and now all my 4 layers have only one attribute, which is ID with a value of 0. As you can see, both the baselines extend beyond the edges of the shoreline. And now we can click on EPR4Q model from the processing toolbox and ready to run the model. There are certain instructions which are mentioned on the right hand side, and you can basically have a look at it and then use the parameters to insert your inputs. I'll keep the default year to be simulated as 2100. The year of my oldest line is 2020. The left baseline on this particular map is the baseline on the land. So I'll click on the landward baseline. The space between points, I've used 7.5. The instructions are mentioned because I'm using Landsat imagery with a 30-meter resolution. So 7.5 or 5 can be used. So I'm using 7.5. The year of newest line is 2024. And I'll link the newest line. Beach angle is the angle of the beach. So this is a roughly 45-degree angle. You can insert this particular angle as per your area of interest. The right baseline is the seaward line, and I will link it. The oldest line is from 2020. In the final 3 inputs that we have to insert is result style final, result style left, and result style right. These are basically the symbology files. QGIS will render the output in a particular format, and these are the files. In the EPR4Q model, the 3 files are already there, and all you need to do is basically link the result files over here. Right. Now these are the only parameters that are needed. We are currently just saving the output as temporary layers. In case you want to save it permanently, you can just click and name and put the path to the destination folder. We are now ready to run the model. Depending on the size of the beach and the capacity of your system, this may take minutes to run. If you have set up QGIS and the layer files in a proper manner, you should not encounter any error while running the EPR4Q model. Occasionally, you may see some red colored warning messages in the log file pane, though you must not be worried about it. It's just something to be ignored. That being said, major errors occur if there is no output that is generated upon the model's completion, or if the model stops abruptly with an error message, or if the rendered output contains certain glaring errors or discrepancies that you can spot. Let me show you the output that has been generated for our model over the Satabhaya village. There is a visual output that has been generated alongside 6 temporary layers. The layers are result layer, the left side result, newest line, oldest line, right side result, and the points layer. Visually, it may appear overwhelming and complicated. It's not like that. To understand it better, let me switch off all the layers and turn it on one by one. The points layer, if you can see, lies exactly on top of the shoreline of 2024, which is the recent shoreline. The right side result are, you can say, some hilly kind of peaks towards the landward side. The oldest line is basically the transects cast from the seaward side baseline onto the 2020 shoreline. The newest line are the transects cast from the seaward line to the 2024 shoreline. The left side result contains a solitary peak but towards the seaward side. And the result layer contains all the transect information with certain color coding. So this is what the visual interpretation of it was. If you open the model again and refer the text mentioned against each of the generated output, there are a few lines written off for it, but mostly it does not make sense as it was translated from Portuguese. You can see in points though, it's important. The shapefile shows the space between points. This result is just to see if some error is there in the analysis. So this should basically get you started thinking, what does it essentially mean? So I prefer to use ArcGIS Pro for analysis and interpretation. So rather than doing it on QGIS, one can do it, but I prefer to do ArcGIS Pro. So if you see the points, there is a attribute table. There is a sum total of 253 points. Even there is a attribute table over here for the right result layer, and there are a lot of columns involved. So let me do one thing. Let me just, for the interpretation part, let me just export the layers. Currently these are in temporary form, so I have to make it permanent and save it as a shapefile, and then I will transfer it to ArcGIS Pro and explore them further and interpret them for you. So I just save it in the destination folder of my choice. I'll fast forward the entire process for all the 6 layers and just show you the output that I have generated, and let me load it onto ArcGIS Pro, all the 6 exported shapefiles. So the output has been generated and loaded onto the content pane of ArcGIS Pro. Let me symbolize it so that it can be interpreted better. So the right side result, which contains all the big peaks on the landward side, I've color coded it as red, whereas the solitary peak on the seaward side, I've color coded it as green. Now what we will do is categorize the layers. It is important to do so that you'll get a better perspective. All the result layers I have clubbed together on top of each other, whereas newest line, oldest line and points, I have kept it as a separate category. Now the reason why I do so is because these 3 layers, newest line, oldest line and points, serve as a validation, a check basically, and the other ones are for interpretation purposes. So if you see that there are equally spaced points and transects across the shoreline. So let me measure the distance between 2 transects. It is exactly 7.5 meters. Now you know already that the entire extent of the shoreline is roughly 2000 meters or 2 kilometers. So if I divide it by 7.5, so there should be there should be roughly around 266 points, which we are basically measuring. So you can see there are 253 points. Our extent was slightly less than 2 kilometers. So there are total 253 points which are basically used for the measurement. If you compare it to the output of the previous workflow using the SAET tool, there were 10 segments of 200 meters each. So now it's a much more granular analysis from 200 meters each segment to a 7.5 meters each segment that will do the measurement. And which is why this tool is much more powerful. It gives a better reading, a better output and interpretation. Even the newest line and the oldest line, you just have to check whether they are equally spaced across it. Now you can see that there is a broken segment over here. But besides that, across the entire length of the shoreline, there are equally spaced segments, both the newest line as well as the oldest line. And just over here towards the end, there is a broken segment. And that is actually because the length of the baselines are not equal. There is a slight gap, and the length of the shoreline also, there is a slight gap, which is why the discrepancy, but it's not a major thing. One can, choose to ignore it. Although if you were to do scientific research, you should basically correct this error. That being said, what we will do now is to examine the attributes, which is the data stored in this layer. So this visual output is there, and one can explore the attributes now. If I open the attribute table of right side result, you can see that there are several columns. There are some total of 501 rows, which should surprise you because the number of points were 250. So this should trigger you that it's actually double counting. It's not exactly double counting, but currently it is not measuring the points data. It is measuring the transect data on both the shorelines. So which is why the 500 figure. And the only column of interest should be the hub distance, which is basically the distance of the transect from the baseline to the shoreline. So that is of the only interest, in my opinion, for this particular layer. Similarly, if you were to explore the attribute table of left side result for the small peaks, that is, there is only 2 rows with the same number of columns, and once again, only hub distance you can basically explore. The other columns are technically not of importance, just in case you want to measure the net change of between the coastlines. These serve as just a visual output. The data attributes are not that important for these particular 2 layers. All the data attributes are actually, which are important to us, are present in the result layer. So you can see there are some total of 254 features, which is exactly the similar as the number of transects. There is one difference, but that was due to the anomaly. So this is the layer which basically contains the difference between the distance of the nearest hub between both the shorelines. So the distance, this DIST, DIF column shows the net erosion or the accretion in the across the transects. So if I sort it on a descending order, you can see that all the values are in positive and there is one value in negative. Ideally, you can multiply it by -1 so as to get the exact erosion and accretion, but I will leave it as it is. Just remember that the positive numbers are erosion because those are basically peering on the landward side, whereas the negative number, because it is jutting out on the seaward side, it is accretion. And these are predictions. So DIST is not prediction. So this is the net, you can say, erosion. So across the spectrum of the shoreline, 13.11 meters on an average is the level of erosion. The visual output, the large peaks that you see, are not related to DIST, DIF. It's basically the result column visualized. And it is because this tool has a analytical component. So you can see 250 meters is the average erosion across the spectrum of the shoreline in 2100, which was our future year of simulation in the model input parameters. So to approximately summarize the output of the EPR4Q model on Satabhaya in terms of the actual net shoreline change, 13 meters on an average per transect multiplied by 2000 meters long shoreline gives us 26,000 square meters or 0.026 square kilometers of net eroded area between the 3-year period of 2020 December and 2024 January. This is scary and should prompt the authorities to respond, because if the rate of erosion continues unabated, in 76 years from now, which is the year 2100, on an average, 500 meters per transect multiplied by 2000 meter long shoreline would translate to 100,000 square meters or 1 square kilometer of the Satabhaya coast to vanish into the sea. I'll switch to a different area of interest now, the Juhu beach in Mumbai, India, which is also reportedly suffering from high erosion. When I started working on the EPR4Q model, I began with Juhu Beach as my initial area of interest only. Satabhaya occurred only as an afterthought after I had encountered errors while running the model in Juhu, and I felt I should repeat the new model over the previous area of interest from SAET and compare both the outputs. Hence, this last section of this workflow will delve into the challenges involved in running the EPR4Q model on certain types of shorelines and how to address it. Here on Google Map, I have zoomed into the western coast of India. In the bustling metropolis of Mumbai lies the very popular Juhu Beach. It's a 6-kilometer long shoreline. I have already set up the project on ArcGIS Pro, and I will show you the results of the model on this software itself. What you can see are the two shorelines of Juhu Beach, which I have extracted from the SAET workflow. The recent shoreline is from 2024, from 22nd of March, and the older shoreline is from 28th of March 2023. So they are just 1 year apart. Let me color the newer shoreline in red. So you can see that visually there is a discernible erosion on the coastline, as was reported in the various news articles that I had initially showed you in this video. Now I have already run the model on QGIS, and for that, remember that we have to export it, convert the projection into the PCS, projected coordinate system of UTM-43N, and subsequently also draw the landward and seaward baselines. So I have already run this output, and I'll show you how the whatever the parameters that I have inserted. So I left the year to be simulated default as 2100. Here, the baseline towards the left this time is the seaward line. The space between transects is 7.5 meters. And the beach angle this time around, I have inserted based on my, you can say, gumption, a 100-degree angle. Rest all things are naturally understandable, so I'll not explain it. Just I've saved the output as shapefiles and have imported it into ArcGIS Pro. So let's begin by seeing whether the model has visually generated proper output. So the points layer appears to be reasonably well rendered. There is equal spaces between the points across the shoreline. Let's see the transects, whether they are proper. The edge over here has several lines which do not meet the shoreline. So that seems to be a important problem. Apart from that, on the other edge of the shoreline also there is several, at least 20 to 25 transects which do not meet the shoreline. So the output will get distorted because of it, and this working of the model is not useful for scientific research purposes. So in comparison, see the Satabhaya coastline. It was a linear shoreline, and the transects were, besides one or two points, it was very well rendered. But over here, the output is not correct. So this is the first level of check where we visually see the newest line points and the oldest line layers. Even in the results section, let me show you a particular aspect. So the distance difference shows you the difference between the older shoreline and the newer shoreline. So this particular point, it is okay. But then if I were to show you another transect, you can see that it does not even touch the shoreline. It is just lying on the satellite imagery on the urban area itself. So the values are distorted, and it would not be a good idea to see the statistics and understand what is the level of erosion. It may give you a good idea, but it's not a accurate idea. And the worst result of them all is the output of the projections. So this is how the left side and the right side results have been rendered. So right side this time, because the orientation of this, it's on the west coast with the ocean on the west. So the left side result is erosion, and right side result is, which is purple in color, is the accretion. So you can see there is a huge levels of erosion which is displayed, and it's not tallying with the shorelines because the current difference between the shorelines is very less, but the levels of erosion which has been projected are very high. So it does not appear properly, and even the angular representation of the erosion and accretion is not proper. So this is, you can say, problematic. We cannot hold the output of this particular model as a proper output or an important output. So I had actually reached out to Dr. Lucas Lima, the creator of this model and this fellow scientific researcher. So he suggested that I should break down Juhu Beach into 3 different segments and run it as 3 different projects. Also, I should draw the landward and seaward baselines very close to the shorelines. And we have had several interactions because I was working on this particular challenge for days, and he kind of gave me some other solution also, just like to extend the shoreline and so on. But then I tried the first suggestion of his, which is to split, because this is a curved shoreline. So there is already, we had seen that this model does not run very well on embayed or curved shorelines. So I had to basically split it into 3 equal segments, not equal segments, 3 segments, which has similar, you can say, angular properties of the beach. And I have done so. So I have split into split 0, 1 and 2. So these are the 3 segments I have divided my project into. So you can see this particular number 0 is the central side of the Juhu Beach. Split number 1 project is on the top side of the Juhu Beach, whereas the split number 2 project is the bottom side of the Juhu Beach. So I have split the entire shoreline into 3 parts and have also created baselines separately, with ensuring that it runs, you can say, as parallel to the shoreline as possible, and also extend both the ends on both the sides, extend much ahead of the shoreline as well. Also, I have created it using the create function. I am not showing it to you. And I had split the shorelines using the split function. I had already covered these tools in my previous workflows. So these were the tools by which I had made the amendment, edit basically. Also, remember that I had converted all the shape files into the UTM zone 43N. This is the UTM zone of Mumbai. So now let's see how the revised output of the EPR4Q model is represented. So I'll begin with project number 0, which is on the central side of Juhu Beach. So this is the baseline. Let me show you the output after just editing the symbology. The red line is the recent shoreline from 2024, whereas the green line is the older shoreline from 2023. The points layer, let me zoom in. You can see that those are equally spaced across the length of the shoreline. So this is the first level of check, that our output that has been rendered by the model does not have any errors. Second level of check is to see the newest line and the oldest lines. So you can see that barring the 2 or 3 lines in the end and a couple of lines in the middle, the transects have been spaced properly and run throughout the entire extent of the shoreline. Even the oldest line, it is similar to the newest line, with barring a minor exceptions, the output has been generated properly. Therefore, we can see the statistics on result _0 and assess what is the level of erosion or accretion on this extent of the beach. 13 meters of erosion has been witnessed in this beach, and that's a very high figure. So Satabhaya had 13 meters for a period of 4 years, from 2020 to 2024, 3 years rather. But then this one is within 1 year. There is a on an average across the 6-kilometer long beach, per point there is a 13 meter of erosion, and at the most extreme it is 50 meters and 60 meters. Now I haven't not factored in the tides while capturing, using the satellite imagery. So do not, you can say the output may be misrepresented, but the rendition of the model is not incorrect. So you can see. So I have validated also by clicking on the attribute. It shows me that the highest risk diff, which is 58 meters, is on the point where I had shown you, where the maximum erosion was. So the rendition of the output is correct, and the right side and left side result, the blue colored ones are accretion. So you can clearly see that the recent shoreline extends beyond the previous shoreline. So it is a good candidate for accretion over the long term projection. So even at this end may be slightly debatable, but then beyond that, even the red line, which is erosion, it seems reasonably accurate. Although in Satabhaya we had a very high degree of projection, like 500 meters of erosion in 74 years, but this time around it is just showing 26 meters of erosion. So I don't know how it has been computed, but then it doesn't seem too far-fetched. So so that is the case. So this was, I showed you how to basically address the issue, but then the central section, the output worked fine. But then let's see how it fared against the lower section of Juhu Beach, because this one is not a linear, it's a non-linear shoreline. It also has a certain curve attached to it, and I tried my best to basically create the baselines parallel to it. But let's see the output of the model. You can straight away see that there are big gaps in the points which have been created. So it kind of gives us a clue that not all is well in the output. Even the newest lines, it mimics the points. So the gaps are very well evident, and likewise for the oldest line as well. So this is a challenge of using the model. So while it works on non-linear shorelines, you need to basically create linear patches of shoreline and then run the model, which would give you the best output. The output is better than the original, you can say, default model, without the splits, but then it's not the most accurate output you'll ever see on this model. So that is about it. And if I see the left side result and right side result, you can see it's not looking very good. The angle is different. So in the beach parameters, on the model parameters, we have to also enter the angle of the beach. So I think the problem also lies there, because the beach is not in a straight line. So it's difficult to find the exact angle at which the model should compute. So this is another challenge. And I believe that to address this, make a better output, you have to split this lower section of the beach into other 3 parts. So in the research paper, Dr. Lima and his colleagues also had problems with embayed shorelines. I'll just show you that section, and they had also proposed how it could be resolved, although I could not understand the meaning of it, but then they did propose. In this section, problems usage of near and filter transect methods to adjust transects to curved shoreline segments. So they proposed workaround, but they recognize that the model is not working very properly on the embayed shorelines. So yes, this was a particular section on Juhu Beach, which I had wrecked days on, and I thought I'll just share it with you.